So welcome everyone to the first non-biomass session. This is the land application session. We have two sessions today. This is the first one. So if you are not for the land application section, you are in the wrong room and you should go downstairs. I will be chairing this session together with Felix Ishundva from the University of Stirling, and my name is Christopher Stier from the University of Ljubljana. We have 5 presentations, so we are quite packed, and I'm happy that the first presenter is already here. And please, Felix.
Yes, so welcome to our first presentation. Elise Colleen will be presenting on the exploitation of X-band Polinsar for high-resolution agricultural monitoring. Elise Colleen is from ONERA in France.
Thank you. Good afternoon, everyone. For those who don't know me, I'm the girl trying to write some blog posts on Medium, trying to make SAR images and also polarimetry more accessible for everybody. So today I'm pleased to present a work conducted with my colleagues about a first insight on what we can expect to find in an X-band image at very high resolution on agricultural crops for monitoring. So first of all, a little bit about the context. We know that, of course, at X-band we are very sensitive to very small spatial details of the structures of the different components. And we can also achieve a very high spatial resolution. But however, we are very limited in depth penetration capabilities. We know that X-band can be useful still for crop monitoring classification, for example, and that we can also expect to find some surface properties from the polarimetric and interferometric signals. But there are still open questions. The first one is we want to see in what extent we will still be able to find information about substructures thanks to the interferometric signals. And also, we want to see in what extent the full polarimetric information can bring something to the interpretation of the structures of this kind of vegetation elements for agricultural purposes, for example. We will tackle this by analyzing 2 different modes. The first one is repeat pass interferometry. What can we expect from this kind of configurations? And the second one is about the full polarimetric analysis. What can we expect also about this structure information? So let's give a small insight in the physics. Most of the properties can be described by the dielectric permittivity in a complex way. So this complex permittivity is very important. It's both composed by the real part, which will be linked to the propagation speed, and which is known also as the refractive index, and also the imaginary part, which is linked to losses or attenuation. Soil moisture controls a lot these values of dielectric permittivities, both in real parts and imaginary parts. And here I have given some, I would say, classical values of these constants according to the relative moisture content of the ground, thanks to very classical modeling of the permittivity of the ground. So what we can see here is that both real parts and imaginary parts are strongly increasing with soil moisture. What about now the modeling or the understanding of the interferometric coherence? So interferometric coherence will be also linked to the dielectric permittivity. And of course, the idea is to better understand what's going on when this dielectric permittivity is changing between the different acquisitions, because the moisture is changing between the 2 dates. And so we can use the modeling proposed by the sun, which gives that the phase, the interferometric phase, will be very sensitive to the relative changes in soil conditions. So it will be able to reveal the differences in soil moisture between acquisitions, whereas the magnitude of the currents will be mainly governed by the the absolute attenuation and penetration into the ground, and will act as an average link with an average situation of the moisture constant. But most of the case, this model was applied to L-band or sometimes C-band image. And the question is how is it changing when we consider X-band images? So we know that we have very shallow penetration depths. However, if we consider the very surfaces layers, we still can achieve coherence that are quite comfortable. I mean 0.5, for example, in this simulation. Whereas the phase, the interferometric phase, will be very sensitive to any soil moisture differences, contrasts between the two dates. So it's interesting because, of course, coherence is definitively low as soon as we will consider penetration depth inside the ground. But on the contrary, we have a very high sensitivity to soil moisture differences between acquisitions. And here we have some results obtained with TerraStar X images acquired in the starring spotlight acquisition mode. And you can see here, it's an interferogram obtained over a location over Palaiseau in France near the Onera Center. And what we can see is that we clearly see very precise spatial patterns in the image of the interferometric phase. With high enough correlation or coherence levels to be able to analyze these spatial patterns. So this makes X-band probably well suited to detect hydrological signatures. And here is a comparison with an historical map that we have on the same area. This historical map contains all the locations of the drains that are very old drainage systems buried inside the ground. And as we can see, the patterns of the interferometric phase are well correlated with this map of drainage structure, even if they are very deep into the ground. So that means that the moisture spatial distribution can be revealed by the interferometric phase, even if it's an indirect detection of some hydrological structures in depth into under the ground. So let's move to polarimetric analysis. Now we consider another images. It's a time series acquired by the airborne SETI system at X-band over Ningaron. So there are quite old images now because they were taken more than 10 years ago. But until now, we still had some difficulties to make the polarimetric calibration in a precise and efficient way. And now we have recalibrated precisely these 15 images. And they are given at a very interesting resolution because we have 40 centimeters spatial resolutions on the ground. I will consider for this polarimetric analysis a description of the ground or vegetation structure as a superposition of different layers, because for natural medium, for me, it's more comfortable to think about what are the effects on the phases, such as what we call birefringence or retardance effects. That means how orientation can modify the effect of propagation on the phase, the relative phase between the polarimetric channels, and also to think about the attenuation effect. That means how polarimetric channels differs on the attenuation properties according to the dielectric permittivity. And finally, what are the depolarization effects? That means like polarimetric entropy, what is the amount of randomness that we can see according to the propagation into the different layers where the scattering occurs. First, for the orientation polarimetric angle, we already know that it's directly interpreted as the de-attenuation orientation effect. That means the orientation in the wave plane of the maximal de-attenuation, the maximal differences between the polarimetric bases. And so we can simply compute from the Sinclair matrix these orientation angles without doing any average to obtain this polarimetric orientation. So just keep in mind that this polarimetric orientation is the result of the projection of the scattering effect, which can come from a 3D component, which is oriented in the 3D space. So for a random case of a 3D cylinder with a strong orientation effect, for example, the orientation polarimetric angle will correspond mainly to this effect projected in the wave plane. So it's directly linked both to the azimuthal angle, to the tilted angle from the vertical, and also to the incident angle on the radar. In the case where you want to consider some structures that are oriented in the horizontal plane, as you can see, the polarimetric angle will be very close to this azimuthal angle with respect to the trajectory direction. But it can also depend a little bit on the incidence angle on the acquisition, even if this effect, like in this simulation, is quite low, especially for conventional orientation angles. Let's move also now to the measurement of depolarization effect. I propose to use here the scattering diversity, which is a parameter which can be computed directly from the coherency matrix. So it's even the same parameter than polarimetric entropy. The only difference, I would say, is that we do not require to compute the eigenvalue decomposition because we can compute scattering diversity directly from the components of the coherence matrix. And as you can see on the simulation, the mathematical representation of the theoretical values of the scattering diversity, it's very close to the entropy, the conventional entropy with respect to the eigenvalues of the coherency matrix. So both parameters are quite equivalent. And we will use it to encode in the future color representation, to encode the saturation value. That means how saturated the color will be next in the images. And what is important also here in this context is that we will compute the scattering diversity by using a temporal estimation instead of a spatial one, because we want to preserve as much as possible this very high resolution that we have in this case. And we will mix effects that are very located in the same pixel instead of mixing sometimes components from different pixels, which can be very bad when we are considering deterministic targets. And so as a consequence, the contrast between deterministic and natural targets is much better when we consider this temporal estimation. So let's move to some results here. First, a quick comparison between what we obtain at L-band and X-band on the same area. So here the resolution is a little coarser. It's 1 meter resolution. And as we can see on small trees and small vegetation areas, X-band exhibits a significantly higher degree of randomness or polarimetric entropy. Even if we have shallower penetration. And I believe this is because the relative sizes of the main components, such as branches, relative compared to the wavelengths, give something which is more complex, especially to interpret, than at L-band, where we see only the main branches, where we can expect to retrieve the main orientation at L-band, whereas at X-band, it's a little bit more difficult. And now results at 40 centimeters resolution is just an extract on the whole image, which is very large. So here are the results of a composition highlighting orientation, polarimetric orientation angle and scattering diversity. As we can see here, the red buildings are very deterministic and corresponds to solar panels, so not very interesting here, but on the most of the fields, you can see a strong orientation behavior linked to the main orientation of the ridges of furrows on the crops. And as we will see here, if we zoom precisely in different crops, we can see a lot of details that appear. And for example, on the pattern on the left, we can see very small and precise differences in orientation distributions and also in scattering diversity, according probably to the stage of the crops. And on the right panel, we can see also still this link of orientation of the furrows according to the trajectory orientation. Concerning the degree of randomness or scattering diversity, we retrieve some well-known results, of course. That is, this diversity parameter can better distinguish between deterministic or different randomness behavior. And when the ground corresponds to bare soil, the behavior is quite deterministic, whereas when crops are growing or on trees areas, we can see that the scattering diversity is much higher. So the scene corresponds more to natural environments. And we tried also to compute what we call the purity index, which give a better insight into the repartition of the different eigenvalues of the coherency matrix to see if this randomness is better linked to a two mechanism or a three mechanism scattering processes. And now our result is that this randomness is mainly linked to a two mechanism component. That would say that this depolarization effect would be mainly due to multipass effects, but in a surface plane, just on the first layers of the scattering, and not to a volume scattering effect. So to conclude, we have seen that interferometry, despite of the very small penetration, could be used to reveal very precise effects in moisture changes, which could be used also to reveal buried objects. That will have an indirect effect on the moisture conditions on the surface layers. And concerning polarimetry, we have seen also that at comparable spatial resolution, X-band exhibits a much higher degree of randomness or polarimetric entropy. Even if the scattering appears to not correspond precisely to a volume effect, but more on a surface effect, but with a lot of multipass effects, and so would correspond to a two-mechanism mixture depolarization effects. So that's it, and I thank you for your attention.
Thank you very much. We have time for one question. Yes? Okay, two.
Thank you, Elise. Very nice talk and also very nice study. It's very interesting. My question would be a little bit, if you think, because we know that with wavelengths, shorter wavelengths, we have a scaling of the roughness. So the roughness component is much, much higher than for longer wavelengths. And in your case, so your depolarization that you're considering here, would it be not something that is influenced by the roughness that you approach within this X-band, which is much, much higher than if you would use L-band, even though, I mean, clearly you don't penetrate so much, but what you're scaling is in principle with the wavelengths is actually the roughness contribution.
I think that both phenomenological interpretation are linked together. I think if you consider what we call roughness, for me, it's just the number of contributing different elements. So it's another view on the object that we are considering. But for me, roughness corresponds to complexity of the main components to describe the targets. And so if we have this complexity, I suppose that we will have also multipass phenomenon and so depolarization.
Yeah, I would agree on this. But therefore, my question is, I mean, because you have a strong contribution of this depolarization or whatever, how you call it, roughness?
Yeah.
I don't know. How sensitive are you really to soil moisture then, if you have this strong contribution of the roughness component, right? This is always a question.
You mean how far I can expect to find such deterministic orientation even if I have strong depolarization effects? I don't know.
Another short question, Kostas.
Elise, thank you for the presentation. You used 40 centimeters and 50 lux in times, 15.
Yeah.
Now, this means 4 by 4 lux. So do you get different results if you make the spatial averaging, if you move from the 40 centimeters to 1.5 meters? If you make a spatial averaging rather than temporal averaging.
The main effects were correlated. I think it was not depending so much on the sample choice, but I have to check further. It's just a first insight, I must confess.
And how you interpret the range effect? Why in far range you lose the color?
You mean the difference of incidence angles?
Yes. In the steep incidence angle it was very blue, and then your randomness was increasing and blurring out the window in far range.
Yeah, we should have a look too. Thank you.
Thank you very much. We have to move to the next presenter, who will be Giovanni Costa. Who will be Giovanni Costa from Politecnico di Milano about estimating soil moisture anomalies. Please.
Yes. Okay. So here we are. Good afternoon, everybody. I'm Giovanni Costa from Politecnico di Milano, and we will talk about estimating soil moisture anomalies via temporal SKP decomposition. Let's start from the introduction, that is the motivation of this work. If you assume to observe a terrain from a satellite, and if you center your attention on a resolution cell, you can recognize at least 2 different scattering mechanisms acting in the same resolution cell that we call ground and latent. The ground is modeling the above ground scatterers that are more temporarily unstable. Instead, the latent is modeling the below ground scatterers, the moisture-related contribution that are more temporarily stable because the variation in soil moisture are slow in time. So, leveraging on this temporal diversity and on the polarimetric diversity, the idea is to extend the concept of SKP to the temporal domain, trying to divide, decompose the latent mechanism from the ground. So, the algorithm takes as input a Polinsar dataset, it decomposes it through temporal SKP decomposition, recovering the polarimetric signature and the structure matrices describing our ground and latent contribution. And to the latent contribution is associated a zero mean soil moisture estimates, so a soil moisture anomaly. Then, given different estimates, we stitch together to provide as a final output the total SMA stitched time series. And we call this algorithm Aqua SMA. Aqua in Italian is water, despite of a C that becomes a K. So the name was forced to be Aqua in the end. Okay, a brief recap about what is SKP. Is an algebraic manipulation of matrices, aims to represent a matrix as an equivalent sum of Kronecker product between simpler matrices. It was firstly introduced to explore the baseline and polarimetric diversity to model for a structure. Here, what we want to do is to explore the temporal polarimetric diversity, so the multipolarization, multitemporal dataset. So, giving some formula, given an MP-MT dataset, we calculate the MP-MT covariance matrix, VK, and what we want to do is to decompose it as the sum of K, number of scattering mechanisms, Kronecker product between RK and CK, that are describing the Kth scattering mechanism. CK is the polarimetric signature matrix, RK is the structure matrix, and both must be Hermitian semipositive definite. How many K do we need? Well, 2 is enough in our case. And in the case of K equal 2, we know that the solution R1, R2, C1, C2 is dependent on a real space solution defined by the parameters A and B. So the next question is how to choose A and B. Focusing on the latent, we want that A and B must maximize the similarity between what we are decomposing and a theoretical model of soil moisture effect onto the complex coherences. About the ground, it must act as a phase calibrator. So what we do is to choose A and B such that the ground is the most triangular scattering mechanism, so the one that is minimizing the phase residues. In this way, we are chaining the solution, basically. Let's move into the analysis of how effectively we choose the latent solution. Among all the possible R2 that are physical admissible, we choose the one that is minimizing, through exhaustive search, the L1 norm of the errors between all the elements of the R2 matrix, so complex coherence by complex coherence, with a theoretical searching grid that is defined by slightly modifying the Francesco De Zan model. So that's T. Then, once RL is elected, we associate the delta soil moisture, the expected delta soil moisture value, we build up a linear system, and we we regress the soil moisture values. Of course, the system is rank deficient, we impose a zero mean condition. So that to pass, let's say, from what we are regressing, that is soil moisture anomalies, to the absolute soil moisture, we need a constant, meaning that our solution is up to a constant. Take-home message, very simple. Aqua does not use phase triplets. We are directly looking into the complex coherences, and then the solution, the estimate is up to a constant. Now, because we know that the effectiveness of the decomposition is much more driven by the number of looks than the number of images, given a dataset of n number of images, arbitrary, we propose to apply Aqua following a scanning window approach, of course, overlapping in time. So, time by time, we open a window of length BW, we estimate the SMA, and we collect the estimate into the matrix of estimates, let's say, and we continue up till the last window is scanned. Then, how to pass from this very temporal redundant matrix to a single stitch time series? Well, through a stitching procedure, leveraging on the temporal redundancy we introduced, we can estimate the offsets among the different among the different window estimates, build up again a linear system, and regress what are effectively the window-wise offset, so that we can averaging them and regress a unique SMA time series of length n. Two important remarks. The stitching procedure is adaptively reinitializing in two cases if SKP is missing the decomposition, so one single dominant scatter is recognized, or if a coherence drop is detected in the considered temporal window. Finally, what Aqua is? Aqua simply consists of an SKP decomposition, the solution is chosen through exhaustive search, SMA is regressed through two linear system inversion. That's it, very simple. Let's move on with the analysis of on the real data. So hydrosoil campaign. It is a campaign that uses a C-band ground-based polarimetric radar to continuously monitor barley and crop. Continuously means that we have an acquisition every 10 minutes. Two measurements campaigns were conducted, the barley and corn campaign, respectively, from March to June and from July to November 2020. It's important here to say that we applied Aqua following a maximally overlapped scanning window approach with a window size of 6 acquisitions, so 1 hour, and considering the entire field as a unique resolution cell because it's quite small. For the sake of time, I'll show you only the barley crop result, but if you're interested on the corn, we can discuss also. Okay, let's start from the first example of estimation, from the 22nd of March to the 29th of March 2020. Bare soil stage, in this case, and every time from now to the end of my life, I said single offset applied, I mean that I used one single constant from the probe for the sake of comparison to take our anomalous estimate and to compare with the absolute domain. This is the first graph this is the first example. On the x-axis you have the date and time of acquisition. On the y-axis the volumetric soil moisture expressed in percentage. The black curve is the probe, the blue curve is the Aqua estimate. The shadow are the plus minus sigma, because we estimated the uncertainty out of the linear system inversion. The green square, yeah, you can see it, are the reinitialization point. So even if, in this case, 2 times the algorithm reinitializes, once for the missed decomposition and the second time for a coherence drop, we used a single offset. And as it is possible to note, we are quite well approaching and following the moisture behavior. Far more interesting is the second example from the 16th of May to the 19th of May. The barley is grow, and as it is possible to note from this estimation is that we are still capable of following the high frequency variation in soil moisture, but it is clear that a low frequency trend is missing in the estimation. What we do, assuming that we never know the ground truth, let's say, we applied Aqua considering a different temporal lag, like 1 day temporal lag. Why we choose 1 day? Because in C-band, the vegetation can be considered mostly decorrelated in 20 hours of temporal lag. Then we combined the 1 day and 10 minutes estimate, and we obtain this new graph. So the orange curve is the 10 minutes estimates, the purple curve is the 24 hours, is the 1 day. We estimated the low frequency missed by the 10 minutes estimate, and we mount it on, without touching the ground truth. And here it is possible to see how effectively we recover the low frequency trend, but it also seems that the estimate is advanced in time. And that's a physical reason, because the probe we have is 20 centimeter deep, and the radar measurement is practically superficial. So we think that this advance is due to a physical reason. Let's move on with the 3 months estimate. We are not masochist, okay? We want to effectively demonstrate the effectiveness of our algorithm of Aqua without cheating, without injecting effectively a lot of information from the available probe measurements. Here you see 3 months of acquisition. The estimate is really raw, considering one single offset for 18,000 acquisition. And I want to point your attention on how effectively we are both following the ripples, the high frequency and the low frequency in the estimation. You see that 26 times the algorithm automatically reinitializes in correspondence of the peak of the probe, so in correspondence of the EV rain, the motivation is due to the missed decomposition from SKP. So that's a quite interesting result, because it's like the rain is completely masking our latent contribution. In the last part of the graph, of the zoomed graph, you see again the effectiveness of the proposed combination of multi-temporal estimates. This becomes even more clear if we consider the last month of estimation. As it is possible to note, while the blue curve, so the combined estimates, is approaching the probe, if you consider the orange curve, so the 10 minutes estimate, it's diverging from the probe, like suggesting that the soil moisture is effectively increasing and not decreasing. When we saw the result, we asked why and what is this behavior. Effectively, by checking the backscatter time series from the hydrosoil final report, you see that exactly in the same period, in the last month, the backscatter is increasing, much more correlating with the vegetation growth, as the free curves, how it works, as these free curves that are monitoring the vegetation, the barley height, and it is instead anti-correlating with the probe. So we were pretty happy, because effectively this multi-temporal combination is helping us to correct, to mitigate vegetation-related effects. Now, this, as discussed, are the default raw result, one single offset over 3 months, neglecting that the algorithm Aqua is telling us, guy, please, I need 26 offset to effectively pass from the anomalous domain to the absolute domain. So, if you are lucky enough and you can inject one absolute value every time the algorithm reinitializes, this is the result you can obtain. And I want still to underline that we inject 26 offset, one per reinitialization, over 18,000 acquisition. So we are not so cheating, no? Let's say. Okay, so let's conclude. Okay. Aqua is a novel polarimetric framework for soil moisture estimation. The core is the temporal SKP decomposition to distinguish, to divide the latent contribution from the other. The structure is super simple, okay, and I was scared about the simplicity of the algorithm, but we demonstrate that even if you remain in the anomalous domain, so without touching the some knowledge from the probe that we never know, basically, we are able to reconstruct both low frequency and high frequency trend. Moreover, we can underline some problem, for example, the EV rains. We have not possibility, at least with Aqua, to recover, to separate between among the contribution, and basically something that can help should be the integration of the amplitude information, because you see peak in the backscatter exactly in correspondence of the EV rain. As outlooks, testing Aqua SMA on other dataset, LP band, and paper in progress in dependence on your feedback, actually. So hoping you like it, and thank you so much.
Yes, we have time for a couple of questions.
Okay, can I write the paper? Okay.
Yeah, thanks a lot. Very interesting, and I think it's a good way to approach soil moisture and also the problem with the vegetation. But I didn't really understood very well how you really corrected for the vegetation here. So was it only a shift, or what have you done?
It's estimate a straight line, like a plane.
But what is if you have a different other vegetation or
Different?
other? I mean, now you have one kind of vegetation,
Oh,
right? It's one
yes,
structure.
yes.
What is if you have wheat, corn, potatoes?
With the corn, I
whatever.
can show you an example.
So you always take one linear shift, or?
Yes, in dependence on the period. Okay. Here we are. Here is 18 days of corn estimates from the birth soil stage to the, let's say, the barley-like corn stage, because it's like 40 centimeter. As you see here in the birth soil, you see that the estimation, the fluctuation are not so pronounced. Then, when the vegetation is start growing, you see that the orange curve is again diverging, like we saw in the barley, and we correct the divergence from the probe. Then, what we cannot and we are not able to correct are these fluctuations here that are, of course, vegetation, where the corn is growing. And these, of course, can be both, yes, transpiration of the plant, we think, and also the growth itself. What I can tell you is when the corn is in the maturity stage, Aqua is no more able to estimate nothing. And we start again estimate in the senescence of the plant here. We are starting following some signal. Of course, with fluctuation that maybe are due to the last brief of the corn.
Okay, then your last result was only a kind of a best example how to shift it for vegetation.
Yes.
Okay.
Consider also we are at C-band, so we can for sure improve.
Costas?
Thanks, very nice presentation. Something I missed is so on the model interferogram as function of the moisture from the slave and the master.
Yes,
it depends on your ground composition, right? It's function of it. How do you envisage to use this large scale, or maybe it doesn't affect that much? Since you look at differential, I don't know, just to understand a bit what is the...
That's a good question, actually. What I did at the first stage, because I know the soil composition for the hydrosoil campaign, was to put me in the worst case scenario. Because, I mean, it's quite fair to think that effectively when you are observing or you are trying to estimate something, knowing exactly the soil composition, it's not true. So for the hydrosoil campaign, even if I know the soil composition, okay, I used some standard value to not cheat. Of course, is it dependent? Yes, from the ULAB model.
Yeah, we have time for one more question. Costas?
Thank you for the presentation. I think it's an interesting approach. My question is, what is your interpretation? Why SKP is not able really to separate the two components? If SKP goes separating the two components, then you will have no problem. This is what.
Sorry, Costas, I don't hear you well.
Why SKP? Where SKP has a problem to separate the two components?
Where the?
SKP.
SKP
yes.
has problem. Okay.
Yes.
In correspondence of heavy rain, and I found your presentation yesterday super interesting. And sometimes in correspondence of block structures. So when you have block structures in the matrix, okay, you both are unable to separate the contribution, and that's super interesting in my opinion, and also you have a coherence change.
Thank you.
Thank you. One more round of applause to our presenter as we move to the next one. Yeah, we'll move to the next presentation. Lorenzo Papale will present from Tor Vergata, will present on explainable AI for soil moisture retrieval.
Thank you for the introduction. Hello, everyone. I'm Lorenzo Giuliano Papale, researcher at Tor Vergata University of Rome. Today I'm showing you this methodology we developed at JPL during my PhD visiting there. So let's start. I will give you a brief introduction about soil moisture sensor data, the motivation behind this work, and also, of course, I'm going to present you the approach, the methodology, an outlook on the data involved and also the study area, and show you some results about how we are able to reconstruct the total backscatter from the components we estimate. We evaluate the estimated scattering components using the radiative transfer model simulations, but also the results of some polarimetric decomposition, and of course the soil moisture retrieval performance. Then final remarks and next step. So soil moisture is an essential climate variable. We know that it has an impact of vegetation health, crop yield, and also fires and droughts. However, measuring soil moisture with probes is time-consuming, and also we don't have spatialized information. So in these, microwaves and SAR data especially can help due to the signal sensitivity to geometrical and dielectric properties of the scene, of what we are observing. So the problem is that on vegetated areas, it's difficult to disentangle soil and vegetation effects on the radar signal. So the goal, the motivation behind this work was to try to solve this problem while implementing an alternative to the global soil moisture retrieval algorithm for NISAR data. And so we consider different actors. So we focused on physical models, and using physical models alone can be tricky due to the fact that they are crop type dependent and sometimes to link to the field campaign measurements used to calibrate the model itself. And if we push the physical model to be more descriptive, we lose something in terms of generalization capabilities. Instead, if we simplify too much the model, the risk is limited representation of the vegetation structure. On the other hand, recent and pure AI algorithms may lack physical meaning and interpretation. So in this context, we need to increase the level of information and the way we use it for our application. So we can play with physical models, AI, polarimetric decomposition, INSAR techniques, and trying to ingest data coming from different sources with some extra data. So in this methodology, we try to combine physical models and AI using also extra data, not only SAR. And here I'm going to describe you the first version, so the original approach we developed. We start from a physical model, which requires detailed characterization of the vegetation to run the forward model. And we obtained a simplified version because we wanted to use the physical model as loss function of our AI framework. So basically we have some scattering parameters, PV, PD, PT, and so on, which refers to the scattering mechanisms, volume, double bounds, triple bounds, and so on. So this will be our loss function. Concerning the AI framework, we start from SAR backscatter and extra remote sensing data. We feed this data in a residual network that we call RTNet, radiative transfer network. And this represents the first task, which is the one of optimizing the radiative transfer model parameters. Then we switch to the second task, which is based on taking the optimized scattering parameters and feeding them in a random forest algorithm to estimate soil moisture. Then we apply basic physical constraints between the two steps to refine the estimation. And this work was published in 2025. Then we moved to a combined approach because we had the limitation that the soil moisture estimation task was after the optimization. Instead, we wanted to blend the two tasks, to integrate them, embed them in a single AI framework. So basically, we have two models. We have the one optimizing the parameters and the one based on a multi-layer perceptron estimating soil moisture. And how we combine them? We use two loss functions, basically. So the first one is the one I showed you before, trying to minimize the difference between the sum of the scattering components and the observed backscatter. But also, the second loss, trying to minimize basically the mean square error between estimated and measured soil moisture. It's worth mentioning that we used, along the inputs, only the HV channel, while the HH channel was used in the loss function. And also we ran 100 models to make the estimation more robust, and we applied the physical constraint to this 100 models. So we kept only the one respecting the physical constraint. Okay, so concerning the involved data, we used the UAVSAR acquisition, 11 UAVSAR acquisition, L-band, from June to July 2012 in Canada, Manitoba province, close to Winnipeg. And we aggregated, after processing the images, to 100 meters resolution. This is because we wanted to push a little bit the resolution of the soil moisture product with respect to the current soil moisture, NISAR soil moisture products, which is 200 meters. And UAVSAR are quad-pole data, but as I mentioned, for the AI framework, we need only HH and HV, but we used the quad-pole data for the polarimetric decomposition. Concerning the measurements, we use MAVEX 12 campaign data. The area is the same, the temporal coverage, of course, is the same, and we have more than 800 soil moisture probes, resulting in more than 8,000 soil moisture samples in the time frame we considered. The major crops are soybeans, canola, corn, and winter wheat, and we decided to exclude the forested areas because, as you can see, we don't have sensors and probes in the forested area, which are the green ones. Okay, concerning the extra remote sensing data, along with the backscatter in HV polarization, as I was mentioning, we included vegetation water content derived from MODIS data, and also some soil composition information like clay, sand, and silt content, and also temperature and precipitation from ERA 5. We aggregate everything, resampled at 100 meters, and we build our dataset. And then we split the dataset in training, validation, and testing as common practice, resulting in using basically the 80% for training. Here we have the first results. So basically, starting from the equation I showed you before, we just computed the scattering components, and by just summing these components, we get the reconstructed backscatter in HH polarization. Here we can see that from a visual point of view, also looking at the patterns in the image, they look really similar. But we also analyzed the distribution of values, and also we performed a pixel-based analysis to understand how close we are to the total backscatter. And we have an average root mean square error of 3 dBs, considering all the days. These refer only on July the 5th. Then, concerning the scattering components, we, of course, applied the attenuation term, which is one of the parameters we are trying to optimize with the RTNet. And we analyzed these components. To to have an idea of how close we are to the real scene we are observing, we tried, first of all, to run some simulation of specific crops, the major crops I was mentioning before, and we compared the results in terms of scattering components between the RT model and our AI framework. And in both methods, we have volume scattering and surface scattering which are dominating, with a considerable double bound scattering and very low triple bound scattering. We notice an overestimation of the volume scattering with our AI framework. Also, we applied the polarimetric decomposition, the Freeman-Darden, generalized Freeman-Darden, and Yamaguchi 4 components rotated. And we try to compare our results also with the results of these decompositions. And the mean values on the scene are in a very good agreement. Still, now with the polarimetric decomposition, these high volume components is in line with the at least with the Freeman-Darden and the generalized Freeman-Darden decomposition. And also we can see with this comparison with the Pauli RGB that there are some areas in which we can recognize that the components are in agreement, like here in the north, where we have low backscatter but high volume fraction, and here we can see that the volume scattering components is much higher than all the other components. And also in the scene we can find other areas where there is an agreement. In some areas we don't have an agreement, so we are trying now to investigate what's the reason. And of course, as a result, the soil moisture maps. We have the soil moisture values comparing the in situ measurement with our estimation. We have a good agreement with a 5% root mean square error and an R square of 0.75 computed on the test set. And this is the map after the inference for July 5th. Then we also conducted a study, a crop-based study to assess the performance, and we noticed that the best performance are reached with for wheat, while the worst are for grassland, and this is likely due to the fact that we have a low number of samples, grassland samples in our dataset. So to conclude, I showed you this physics-informed approach, trying to combine physical models and deep learning to represent the phase matrix, so the vegetation structure and the attenuation effects. And we validated using this MapVex 12 campaign, and we reached good agreement in terms of reconstructed backscattering HH, and also the component seems to be physically consistent, at least for a mean value point of view. Of course, we are going to conduct more robust analysis, like field level analysis, looking at the whole time series we have. And soil moisture retrieval seems to provide good results, as I was mentioning before. And the next step are to move to spaceborne data. To be honest, we already start with the LOS2 data, but unfortunately, we are using USDS in measurements from the Department of Agriculture, and their policy didn't allow me today to show you the results, but we are working on a paper. And also, of course, to apply this methodology to NISAR data, and we are trying to understand also how to extend the study to P-band data, to how to integrate it with L-band. And considering the improvements, yeah, they are a lot. We want to add some physical constraints, because sometimes it can happen that the scattering parameters are swapped. Also, we want to refine the scattering loss and try more deep learning architecture. So this was my last slide, and thank you.
Thanks, Lorenzo. Thanks, Lorenzo, for this interesting presentation. We do have time for some questions. Otherwise, I might start. Sorry, Irina. So you have used a lot of, you said extra remote sensing data. Have you done any feature ranking or the analysis of their contribution to the accuracy?
Thank you for the good question. Good point. We didn't start, but yeah, the feedback we are receiving go in that direction. Because sometimes scientists are asking, okay, you are including, for instance, also precipitation. Yeah. So we want to understand how each input feature contribute to the final estimation. Of course, like precipitation or temperature are 10 kilometers resolution, while we are doing estimation at 100 meters. So we think that's SAR information, but also the vegetation water content and soil composition data contribute more. But of course, we are going to do a ranking analysis.
Thanks.
Thank you.
Irina. Okay.
Okay, thank you.
Give the mic.
Thank you a lot for your presentation. And my question is, in this study area, we have the UAV SAR data set with a large range of incidence angle, right? About 20 degrees to 63, right? And when you train your model, what do you do with the different incidence angles? Because maybe the polarimetric features are very different in different areas. And my second question is, I think this area have about 14 images, about 14 days of the observation. It had a different crop growth stages. So when you're training your data set, how can you figure out or how can you set your training data set regarding the crop growth? Thank you so much.
Okay, thank you. And concerning the incidence angle, we process the SAR images at the beginning, normalizing the angle to 40 degrees. Of course, it has an effect on the acquisition and also on the estimation. That's why now it's not considered like an input features, or we don't train different models following different angle intervals. But for sure, it's something we are considering also because we want to use multiple sensors and spaceborne data. So, for instance, when we model the surface surface component, we have two parameters which are PSB and PSA, and this was to take into account the for surface, the soil roughness, but also the effect of incidence angle. Now it was normalized, but what we want to do is to include for all the components is to propagate this information to the whole physical model we use.
Okay, thank you.
Thank you very much. Irina, you will, okay, thank you. So we are moving to the next presenter, who is Henry Schauer from DLR. He will be speaking about limits of soil moisture retrieval at L-band. Please.
Yes, good afternoon from my side. I'm Henry. I'm working as a doctoral researcher at the German Airspace Center, and as just introduced, I will be talking about limits of soil moisture retrieval at L-band over bare and vegetated fields using airborne polarimetric differential SAR interferometry. Another title could be masking soil moisture estimates with copolar phase differences. So there will be about a small experiment I conducted. So it's a phase-based methodology. And I think the first talk already gave quite a nice introduction on this using phase for estimating soil moisture. We also saw on these slides the model from Francesco De Jan, and there in correspondence, in the same time, Simon Seeberg developed another model which incorporates two more parameters. That's the volume to surface ratio F and the soil profile A. So that's a bit more of a complex model, and we can account for some more variations in the soil. But, and that's very important, our models assume that it's bare ground, right? We cannot deal with vegetation. And in our geometry, so it's a repeat pass zero baseline constellation, right? So a change in soil moisture or soil wetting will result in an increased phase. That is a increase in distance to the sensor, so basically an error in our DM estimation. That's how one could put it. Right. So we would have to find a way with dealing with that vegetation. That's just a mathematical formulation. We can see that we've got basically a volume contribution and a surface contribution. These are the two terms in equation 1. And in that volume contribution, we have our volume to surface ratio. So adjusting, if it goes to infinity, our volume term will dominate, so the subsurface contribution. Right. Generically, a change in soil moisture will induce a change in the soil dielectrics, and then also a change in the vertical wave number. Right. We also have a first-order surface contribution in here based on the Fresnel transmission coefficient and Snell's law. We can look at our scattering vector, and we can see that we can deal with HH and VV polarization. That's also an advancement compared to the model from Francesco De Jan. And today we'll be looking mostly at VV polarization. Right. We need to parameterize the model somehow. I decided on a root mean square height of 1 centimeter. That's the roughness of the soil. And I did a couple of independent forward model runs, and then decided on an average volume to surface ratio of 10 and a very much neutral soil profile, meaning that the change in that volume is coming from all heights similarly. So neutral soil profile, volume to surface ratio of 10. This plot already, I think you saw it 2 times already today, so plotting one against the other soil moisture value as a function of coherence and phase. And we can see that the more the moisture values differ, the smaller the coherence is, and the higher the phase is. That is logical and to be expected. Just a quick example, changing moisture from 10 to 20%, we can see a coherence of 0.51 and an interferometric phase of 58.3 degrees. That is at an incidence angle of 45 degrees and a sand content roughly 30% and clay content 23%. Right, so we are sensitive, less sensitive, as you've seen before maybe, compared to X-band, but still very much sensitive enough to estimate soil moisture with these models. What data are we using? There was a campaign conducted by DLR and some partners in early 2025 from April to July. And it was quite an extensive campaign, 23 acquisitions, and we are seeing some of these acquisitions here. And important to note, the idea was to first have a lot of bare ground in April, and then successively, with more vegetation on the fields, being able to cover the whole crop growth season. So we can see in the first image, so poly RGB, more surface scattering, and then successively more volume and dihedral scattering. Our area of interest we'll be looking at today is Eitelsried. I'll use the pointer located here. And that's actually the maize field, potato field, and that's the wheat field. We'll be looking at in a second. But more about the campaign will be presented by Rena tomorrow from 9 to 10:40 a.m. in the Red Hall. Right, looking at our AgriROS-L SAR data again, as I said, 23 flights. We've got polarimetry, quad pole, interferometry. Our separation is in accordance to Sentinel-1 and ROS-L, 6 days, and we can also conduct tomography. Spatial resolution is at L-band 60 centimeters by 1.3 meters. And now importantly, looking at the ground data, we can see that the maize and the potato field, they are still kind of bare in the beginning of June, whereas the wheat field, being winter wheat, is already vegetated mid-April. Right, soil moisture was measured every 50 meters for every flight for these 3 crops, and we also measured the vegetation height. There were additional parameters covered by LMU Munich, but they are not available yet, so I couldn't do any forward vegetation modeling. Right, so let's jump into our model inversion. Right, the final goal is to estimate soil moisture, so we have to do some statistical optimization to find the soil moisture value that best predicts our reference EFSA data. We fix the first moisture value because it's basing on the interferometric change information, right? We have to fix the first value at 19% in our case as an average between all fields and all dates. And then we optimize the other n-1 moisture values to minimize the loss L. We build our optimization on the phase triplets and on the coherence, both, but we don't perform any weighting of these 2 contributions. The phase triplet I won't explain in too much detail, but it helps us exclude these atmospheric and topographic influences. Right, so just taking 3 of these acquisitions and calculating them in a loop. We use an atom optimizer, 300 iterations, and we also perform multi-looking to get a stable phase. And we've tried 100 looks and 600 looks, and the impact you will see in a second. We apply it to 2 different periods, that is only bare soil and then the whole, in this case, 15 dates I am using. Right, so let's go to the first results and just understand or start to understand what's happening. We've got our observed closure phase here in VV in the top row and our modeled one in the middle row. And we can see that we have got various environmental processes happening at the same time, right? Not only soil moisture changes, but also, for example, here, there has been quite a lot of drilling that took place at that time step. We've also got forest that is right here on top. By the way, I can't forget to say, red is the cornfield, potato is yellow, and wheat is the blue one. That's important for you to know. And here we've got vegetation growth starting in the end of May, at least on these fields. And what's important to know is that the scaling here, we are looking at from minus 100 degrees to plus 180 degrees, and soil moisture changes usually take place, let's say, between 0 and 60, for example. So that's not that visible here, but they're also included. And we can see that when modeling, actually, we've got an underestimation of the phase, but that's true for all dates, but that's not a problem in that sense, because our phase, our physical model also flattens out. So when going to these larger soil moisture changes, the phase doesn't change that strongly anymore. That sort of Milky Way pattern we are seeing here. Right, so our model kind of nicely reproduces our observed coherences, but doesn't capture the dynamics or the extremes as well. But yeah, looking then next at the coherence, the predicted one, we can see again that the patterns are captured quite nicely. We can differentiate the different fields and the overall level. Also looking at the scatter plots, that's a logarithmic scale, so most pixels are rather at this one-to-one line, but still the spread is quite large. And what's important to note that the noise here in our maize field and also in the potato field compared to the observed coherence is quite large. And that is problematic, of course, as we are looking mostly at maize and potato. And I have to say, if doing the optimization only for the maize field alone, only for the potato field, only for the wheat field, we can get rid of this noise. But there's different reasons, so at least that's my interpretation. We're also having, so first of all, it's a very mixed scene. We've got forests, actually also a small village here, and furthermore, very much low coherence values. Then on the maize field, we can also see these stripes, and these factors also, then in the end, calibrating the model itself results here in this noisy structure. Right, just for you to know, and that's also an explanation then why we are seeing a large spread in the estimated soil moisture. Top row is the reference soil moisture, and then the middle one, the model soil moisture, and all in all, we can say that for some dates it works nicely. For example, the 27th of May, we can see that the overall level is captured quite nicely. Correlation and metrics are not really good, but the talk is not too much about these metrics today. But we know, at least for some dates, the model captures what we want. Right. So this is just another way of calculating it with 600 looks, so more averaging, and that pushes these rather spread out estimates a little bit more closer together. Right, so let's move to the experiment. So we want to quantify vegetation. We're looking at the copolar phase differences for that. And we've got our complex coherence between these two channels, HH and VV. And then we can use CPD as an indicator for these various scattering mechanisms. The physical mechanism behind that is birefringence, so the polarization-dependent phase delay, as the radar wave propagates through the vegetation. Anisotropy describes basically the same phenomenon. Right? And because crops are a highly oriented medium, not all of them, but many of them, we can use CPD to describe these crops. And what is problematic that if there's a lot of volume scattering, because that works as a depolarization mechanism, right, for some crops, if there's a lot of volume scattering, CPD really is very unreliable as the sensitivity is lost. Case studies have shown that for rice, barley, and corn and canola, these CPDs can be used. And that's just a short overview of the ranges of CPD we can expect. For birefringent media, overall it's -10 to -170 degrees. For corn, that's very similar, so that's the typical example here, -20 degrees to 170 degrees. And then for all these other crops, we have sometimes very different CPD values, so finding an optimal threshold is not so easy. Surface scattering would be 0 degrees, dihedral scattering 180 degrees, right? So we just decided on a sort of average threshold from -100 degrees to +100 degrees to perform our masking. So we have our observed closure phase and observed coherence. Then we calculate our closure phase, and with them we perform our masking. So before the inversion, and then input our masked coherence and masked observed closure phase and masked observed coherence into our optimizer, and then retrieve our best soil moisture map, which we can then hopefully trust a little more. Right, looking at the CPDs, we can spot that for the first couple of dates, because it's mostly, at least for the maize and the potato field, mostly bare ground, there's not too much happening. And then as we enter the vegetation growth period, we can see there's more colors coming in, more negative phase values for the maize, because the VV signal is much stronger than the H signal. And then, looking at July the 15th in the end, we've got the strongest negative copolar phase differences. So that's actually quite promising. So we can use it at least for some crops for masking. That's just another way of putting it. We've got our height of maize here, and the copolar phase differences, they follow the height quite nicely. For potato and wheat, that's wheat and that's potato. It follows it a bit less nicely, as we also just seen in the metrics. Right, so again, looking at bare soil, now the masking has taken place. We can see that actually not too much masking took place. So here, that's the first date, that's why that's fixed at 19%. Here there's some masking, and then going to the 27th of May, 3rd of June, we already see that some fields have been masked according to the copolar phase differences that is calculated over here. And again, the change here, because there's not too much masking in the scatter plots, isn't too big. That's a different story for the vegetated surfaces, and here we can start looking at masking at the 9th of July and the 15th of July, for example. And here the maize field is basically completely masked out, and that's a bit of cherry picking, but still I think we can use it to see the potential of the method, is that we see a 7% higher correlation. So here, looking at the red cloud, that's basically completely masked away. So that's in accordance to the high CPDs in the crop and the corn field. Right, so there is some potential, and I'm coming to the summary. Our model assumes the bare ground and requires careful calibration. That's very important, as we've seen. Our change in phase and coherence is always interpreted as soil moisture, so we have to differentiate what mechanisms we see. There's quite some problems with the spatial ground conditions that are not considered, so the surface roughness can be changing every couple of meters. Also, maybe not the soil type, but these inhomogeneities in soil composition and density, they influence our measurements. We have to question how robust our relationship between the in situ data and the radar measurements are. So integration depth, also the interpolation we are choosing. But in the end, CPD is a promising metric, at least for our birefringent media, but the masking threshold is not really universally applicable. So we would have to find these thresholds for every crops individually. Right, so a volume scattering indicator would be nice. And summarizing, we can say the interferometric phase is sensitive to soil moisture change. However, the models need to be adapted to account for adaptive roughness in vegetation. And finally, then, we could start thinking about just adding CPDs, for example, as an uncertainty measure in the metadata. That's another approach compared to masking. We can also find other indicators to mask this volume away, and that could also be amplitude-based approaches or observables, just like the alpha angle, for example. The final goal in this analysis is to go to a sort of surface-to-volume separation, for example, including these differential CPDs that are portrayed here, so the change from date to date, from the contribution of the vegetation growth, and then integrating it into estimates into a physical model that then can also estimate the vegetation part, and then finally gives us a better estimate under vegetation. Right, that's it. Thanks.
Yeah, thank you, Henry, for the presentation. We have time for a couple of questions.
Okay, then I will start with the first one. You at the end said that you should estimate the influence of roughness and vegetation. Which one is more important, do you think, and how big is it?
Yep, so at L-band, the roughness is not as important as for C-band, right? So I would argue that definitely vegetation has a bigger impact into our total signal, because the amount of moisture in vegetation, I mean, it depends how high the vegetation is, but it's really crucial, and therefore, also because we can account for the surface roughness already in our models, dealing with the vegetation is of bigger importance to developing these models right now.
Thank you. Any other question? Okay.
There we go. Thank you very much. Since it's L-band, I mean, I would expect that the type of vegetation has kind of a major kind of impact, right, on the backscatter. So maybe for potato, which is very low, I don't know, maybe and it's kind of sparser, then I think maybe the soil roughness might still have an impact. I mean, if you take, say, like maize or something like that, just really big, you probably have very little kind of impact of the roughness. But I think that, I mean, our experience with ALOS Pulsar is that kind of surface roughness and the directionality of the fields that actually has a quite significant impact. I actually don't really know kind of how that kind of decreases as the vegetation grows, though. So but I actually had a question on one of your last slides where you talked about kind of maybe one of these. You were saying that the masking had kind of you had different influence of the masking. How can you see that? Is that how would you see if the masking is, say, successful or not in the image here?
So that is definitely so. As I said, definitely cherry picking in that sense, because for many dates, so I would argue that we are looking at a subfield sort of. So 100 lux, it's maybe 3 by 3, 4 by 4 meters. 600 lux is then maybe 20 meters by 20 meters. It's still very much subfield. So the averages look definitely better. So there, if we would just compute the metrics between the dates for our average values per field, they would already increase. So for all of these fields, right, we can look at the correlations, and they're not really good. Also, the RMSE is not really good. But just looking at this field here we can see that when we mask out our maze field based on the CPDs, we remove parts of the estimates and then end up with a 7% higher correlation. With the 600 lux for 100 lux, that would be 20% higher. So it gives us just an idea of how much vegetation vertically oriented is on the field.
Okay, so there you would say that you would have successful masking
Yes.
in
Yes.
those last. Okay.
But the question, in the end, it will definitely be like how long, at what point is there still some signal from L-band on the ground, and when does it saturate, and is it maybe already like there? One would need to empirically then check the different fields and see at what point there still is some signal from the ground and how it corresponds to the CPD values of the different crops.
Okay, but for all the 3 crops, the values are better, right, in the last row, right, or last column?
So
because I mean, all the 3 different colors are kind of higher there, so so that's kind of good, so to say, I suppose. Is that right?
I mean, if they are much higher, I'm not sure about it. I think it's rather the same in that sense, underestimation from the model, but due to the masking that we can have a bit more trust that these results are viable.
Okay.
Yep.
Yep, thank you.
Thank you so much. Yeah, we'll move on to our next and final presentation by Nikita Basajin from DLR, and he'll be presenting on soil moisture estimation from L-band Polinsar.
Yeah, thanks for the introduction. Nice to be here. We are essentially staying in Bavaria using the same test site. However, we are moving from interferometry to polarimetry. Right, so the motivation for us is still quite similar to the previous talk. We are looking into soil moisture estimation from SAR data. But as you have already heard a couple of times today, very often the main challenge is the presence of vegetation. And to address this, we are essentially doing 3 things. First, we are using fully polarimetric data to separate the ground from the vegetation. Then we are using L-band to have a better penetration to the ground. And the last point is we are using a time series instead of single acquisitions to have better information of what is changing. So let's start with the data. Essentially what we are doing is a quite simple processing. So we take the SLCs and estimate the coherency matrix for every pixel. And we don't only do it for one date, we do it for the whole time series. And then essentially we stack this into a time series tensor, which you actually can see as a subset of the data of the temporal SKP, if you remember the talk from Giovanni. So essentially it's just the diagonal part of the full multi-polarization, multi-temporal matrix. Now we have the data. The question is how do we connect it to actually soil moisture, right? And for this, we are using physical modeling. We have one component to model the surface scattering from the ground. So it's essentially a physical model that takes 3 parameters and predicts us the expected SAR signal. Then the second model is modeling dihedral scattering. Again, several parameters, in this case 4. But actually soil moisture is shared between the 2, so it's the same. And finally, we also need something to model the volume scattering from the vegetation. And for that, we're using quite simple model, in this case, random volume scattering. So if you now look at the parameters, we have in total 7 of them. So the forward modeling direction is quite straightforward. You just take your parameters, put them into the model, and you get your prediction. I should also note that the models assume reflection symmetry. So the covariance matrix that you get has a couple of zeros. So in total, you essentially have 5 observables, but your model has 7 parameters. So the forward direction is clear, but the inversion, of course, is ambiguous because you cannot estimate 7 unknowns from 5 observables. There are several solutions, and you don't really know how to pick one. There are several ways you can do to address this. What people often do is just simplify the model, set some parameters to constant values, and invert the rest. in our case, we are doing something slightly different. Since we have many parameters, we also need more observables. And what we essentially do is we look at time series to expand the observation space and have the ability to invert the model. The important part is that you have to share some parameters over time. So basically, these boxes are constant over time, and these factor parameters are allowed to have different values for every time step. Now, to summarize the forward model, you start with the parameters. Some of them are constant over time, others are varying. Then you plug them into the physical models to get your three components that model surface, dihedral, and volume scattering. Then you sum them up to get the reconstruction. And now, essentially, your goal is to have your reconstruction as close as possible to the actual data that you observe from your SAR sensor. How can you do it? In our case, we are running numerical optimization. So we are setting some starting values for the physical parameters and then optimize until we basically converge in order to obtain parameter values that give us a reconstruction that is as close as possible to the data. And if you now check the number of parameters, we have essentially three parameters that are allowed to vary over time. So that's 3n unknowns, and then also these 4 boxes plus 4 in total. But we have 5 observables, so this makes this inversion problem mathematically tractable. So I guess the test site looks a bit familiar to you. Was shown previously by Henry. We are focusing on the 3 test fields in this area, which were sampled by actually our group. There will be more data from this campaign coming later. We don't have it yet, but I'm already quite curious what kind of stuff we get. Again, a more detailed presentation about this tomorrow by Irena. So now we have the data, we have the method. Now the question is, how do we actually validate the metrics? We have ground measurements for that. And I just briefly want to describe how I basically compute the metrics, because I think it's quite important. So essentially what we do is we run our methods. We get an estimation for the soil moisture, so basically for every pixel. Then there is a masking step, because we have some criteria where we know the predictions are not reliable. And then we basically take the ground measurements and sample at the positions where we know what the actual soil moisture is. And from that, we can compute the metrics. What I'm doing here is I'm averaging all the data that we have over the field in order to get the mean trend and the standard deviation for the field. So the metrics you will see are basically field scale and not pixel-wise. Right, so let's go to the first field and have a more detailed look. As you can see, that's maize, that's growing quite a bit. So over the whole duration of the campaign, we had 23 flights. And what I'm plotting here at the top is the Pauli RGB time series of the field. The field is here in the middle. As you can see, we are starting with basically blue, which means surface scattering, and then as the vegetation is growing, it's getting more reddish and greenish, so more dihedral and volume scattering. For the maize field, the plants started growing somewhere in the middle of the time series, and then towards the end of the campaign, the vegetation was quite tall. So if you look at the vegetation height, we have about 2 meters in the end. So that's quite a bit of vegetation. Now, if we run our standard inversion method, we developed it for the previous campaigns, and we just took the same parameters and just ran it on this longer time series. We got following results. So in blue here, you have the ground measurements averaged over the field, and in orange, that's basically the estimation that we are getting. The first obvious thing that you see is that there is a general underestimation here. The standard deviation is also quite high. That's why averaging over the whole field is helping quite a lot. But you also see that the general trend is captured quite nicely, I would say. So you basically follow the general trend. But you also see these kind of 2 outliers. And if we look a bit more detailed into the data, we know that between flight 3 and 4, there have been some preparation on the fields, so the farmers planted the crops. So essentially, the soil roughness was changed, but our model is assuming that it's constant. So that basically leads to this, this peak. So what you can do is to address this, first, you can play around with the model parameterizations. So if you increase the number of look and use a different volume parameterization, you essentially can get closer to the original trend. But in addition, if you know that at some point the soil roughness was changed, and you, for example, can detect it just by looking at the coherence between the two dates, and if you cut the time series at these points, your results get much better. So in this case, we are following the trend quite nicely, and the bias almost disappeared. Now we have another field, potatoes. That one was, I would say, quite tricky, because if you look at it, it's not even really flat. You have these kind of row structures that are about 80 centimeters apart, and the depth changes about 25 centimeters. So we were not even sure how well we will perform here, because our models assume basically a flat surface, right? So again, at the top here, the Pauli image of the crops, you can see a lot of green in the end. Potatoes are growing. For the first acquisitions, the field was actually quite flat, and then between the first and the second, the potatoes were planted. So that's where you start getting these row structures. Right. Again, just to show you the vegetation development over time, we had quite a few dates where there was no vegetation, and then it starts growing. And again, we can run our model basically on this field. And as you can see, there's again a quite strong underestimation for the first date. Now we tried to play with the volume parameterization, and in the case of potatoes, it was not really helping. So using vertically oriented dipoles was actually making the results for the end a bit worse. So it looks like for potatoes, random volume is working better. And in case for potatoes, cutting the time series into several chunks was also not very helpful. So I would say that's more of a challenging crop types. Then the final field, wheat. We have essentially the time series over it as well. For the first acquisitions, it was already starting to grow. Was quite low, but still the vegetation was already there. And then as the time progresses, you can see we get quite a bit of dihedral scattering. And then towards the end, when the plants are starting to dry out, they basically start to become more and more transparent to the radar. That's why you again see more blue, more surface scattering. And again, just to give you an impression about the vegetation height, we get this time series here. Now, if you run the model, again, we see some underestimation with the standard settings, but once you start to tweak it, so first you can change the volume parameterization, and we see that the bias is getting less and the accuracy improves. And what you can also try to do is to cut the time series. But in case of wheat, I would say it was improving a bit, but not too much. And I think the main reason for that is that for this field, there was no significant change in soil roughness. So our assumptions are mostly valid. So you can also work with the whole time series and you achieve similar results. All right. This already brings me to the summary. What we can see that the general field scale soil moisture trend is well captured. And even though we have quite a lot of vegetation, since we're using L-band and using polarimetry to separate ground from the vegetation, the retrieval is possible. But of course, there are still a few remaining challenges. For example, we could observe that depending on the crop type, different volume parameterization works better. So it could be useful to have some additional criteria how you choose the volume model, or maybe combine it with crop classification approaches to have crop-specific models. And we still have this general soil moisture underestimation, so this is something we'd like to look more into details. Just referring to the previous talks, I think polarimetry has quite a bit of potential if combined with interferometry. So would be quite curious to combine it, for example, with the temporal SKP, just to get a better sensitivity to changes from interferometry, but also get absolute moisture estimation values from polarimetry. We are currently working on a paper, so hopefully get it out soon. But if you have any questions, I'm also happy to talk to you in the coffee break. Thank you.
Thank you very much. We have time for a couple of questions.
Thanks for the presentation. You mentioned this a little bit, but what is the metric that you use for choosing the volume? Is it because your soil moisture gets better, or do you have something else to look at and they say this is the volume model?
So basically for the standard inversion, we were using the most generic type of volume, so just random volume scattering. And then we thought, okay, what happens if we change this model to another one? And we saw that it improves, but we didn't do like a specific study on how to choose it. In the paper that's coming out, we have an idea to estimate the volume from the data. So essentially what we do here is we fix the volume and estimate soil moisture, but potentially if you have enough ground measurements, you can fix the soil moisture and try to estimate the volume. So this would be quite interesting to run for different crop types and see what kind of volumes match best.
Thank you.
Thank you. Any other question? Then I have one. You have mentioned maize, potatoes, and wheat. Are those the main crops in the area, or will you expand the study to further crops, and what do you expect?
Yes, so I think wheat and maize are quite common. We also have some other campaigns where they are quite dominant. But the campaign, and I think Irina will tell a bit more tomorrow, is quite large. So we are still waiting for some data from our colleagues, which will include also other crop types. So I showed one slide before where we essentially had additional test fields. So I think more like 5 or 6 additional fields where we have soil moisture ground measurements. So there should be more.
Any other question? No? In that case, I would like to thank you again.
Thank you.
And thanks to all the presenters. We are right on time, so we have time for coffee breaks. And remember, the next Lent session starts here in 20 minutes.
applications. I'm Alberto Alonso González from the Technical University of Catalonia, and I am here with Elis Colan from ONERA. We will have 5 presentations and a lot of polarimetry. So the first presentation will be given by Felix Isundar, and with the title, Using Ground Synthetic Aperture Radar to Simulate Multi-Frequency Backscattering from a Fluid Environment.
Thank you for the introduction. Yes, I'm Felix Kasiti Sundwa, currently a PhD student at the University of Stirling, under the supervision of Armando Marino and other co-authors whom I would like to thank, who are listed in this first page of my presentation: Andrea, Isabella, Peter, Claire, Thiago, and Juama. Today's talk, or the first part of my talk, is going to center around the utilization of a ground radar to understand how the radar backscatter signal evolves in a flooded environment, and to understand how this also behaves in a different polarization, different frequencies, moisture conditions, and flood depth. So the focus is to understand the transition between different flooding scenario and how that can be observed from a synthetic aperture radar perspective. So in this experiment, we utilized a ground radar, a vector network analyzer, with the capability of acquiring data from 1 to 12 gigahertz, or 1 megahertz to 12 gigahertz. This VNA was fitted with 2 duopole antennas, so together they give a capability of acquiring fully polarimetric data. And the radar, together with the antenna, were fitted on a platform, which we are calling a rail that is around 4 meters long. But the platform and the radar moved a distance of around 3.75 meters along the rail. And what controlled the movement was the motor and a stepper motor with the programmable Arduino code Arduino. We had 3 different targets fitted around the tank, and they were fixed there during the entire period of data collection. And this would help us to understand or calibrate the data. So it enables us to understand the different scattering mechanisms, and also when we are calibrating how that appeared or performed. So this is how the setup of the experiment was. So the VNA was fitted on this moving platform, and we acquired data while moving forward only. While the return movement, we didn't acquire any data. So in a satellite perspective, maybe we could call this as an example of ascending orbit, for example. And as I earlier mentioned, the 3 targets, we had the metallic plate in the middle, a tilted dihedral to the left, to the right, and a dihedral on the left. The tilted dihedral was at a 22.5 degrees rotation in azimuth direction, and around 45 degrees in line of sight. Our tank was measuring 3 meters by 1.5 meters long, and with the variation of incident angle of acquisition from the start of the tank between 12 degrees to around 55 degrees. We tested different variables. So the first is we grew grass on the tank up to around 50 centimeters and acquired data from 1 to 10 gigahertz with the 1 gigahertz interval. And we tested different variables such as when there is dew I will show you the next slide. When it's dry, when there is dew, when the soil is wet, or when the soil is saturated, or when the soil is partially flooded, so this simulates flooding under vegetation, or when the tank is completely filled with water, both when there is no grass or when there is grass. And also we removed all the grass afterwards and acquired a couple of measurements when it was dry, saturated, and flooded. So the entire campaign collected up to around 40 data sets per frequency. So between 1 and 2 gigahertz, we acquire around 40, but we have up to 10 gigahertz, so a total of approximately 360 data sets. But I'm only going to present 12 data sets for this presentation, ranging from 1 to 2 gigahertz. So this is how some of the tests were. So the first, what we're calling dry, is when we have grass, but we do not add any water, and we just acquire the soil moisture measurements. Then we have dew, we just spray some amount of water to simulate dew on top of the grass, but that does not a lot to change the soil moisture condition. And this is an example we're calling completely flooded, but we have two. So when there is grass, there's still some emergent grass, but when the tank didn't have any vegetation, this is how it appears. How the experiment was carried out. So the first thing we did was, or the process is to vary the soil moisture parameters or water depth, then acquire data. We've acquired a fixed number of data sets in range 259 data points, and in azimuth, this was frequency dependent. So between 1 and 2 gigahertz, around 120 points in azimuth. But when we get to, let's say, 9 to 10 gigahertz, we acquired more data points up to around 300 or 400 points. And then we focus this data using a time domain back projection. And then we utilize the 3 targets to do calibration, polarimetric calibration, and we applied a simple radiometric calibration using the targets. Then after that, I'll just show an example of some of the analysis. So we decomposed the data into a coherency matrix and performed 2 change detection methods, so optimization of power difference and the ratio, which I'm going to talk about. So this is an example of just showing the decomposition. So we apply the Pauli decomposition. One of the models that we applied was the additive model after decomposing the data. The model is optimization of power difference. So this is the difference between the 2 coherency matrices, one acquired one before and one that we have flood. So in this case, we use the first image we acquired, or the first data set we acquired when the soil is dry, against all the other data sets. Then we also applied another change detection method, optimization of power ratio. This gets the ratio of coherency matrices between different acquisitions. This method was proposed by Amando and Nanini a while back, and it's referenced here. So the preliminary results, so the first variables or the test we did, we had a dry, what I called dry earlier, with around 2.5 soil moisture measurements, and then the dew, we didn't change the soil moisture. Then when we added water to the tank, we had around 3.7 soil moisture. And then flooding conditions, we added water to a point where the water was above the soil but below the grass, around 10 centimeters, 17 and around 20. Then what I showed earlier of a complete flood. And then when you remove the soil, when we remove the grass, we had around, we measured 3 or 4 measurements. So this is an example of one of the measurements when we acquired data between 1 and 2 gigahertz. This is what I'll focus on for this presentation. We have the 3 targets just to show us or guide us how the performance is and how the calibration went. The yellow bounding box is what is the area covered by the tank, but the orange is what we selected for the analysis because we see there's some interference from the targets. I'll just draw your attention maybe to these two measurements. Is where we have a complete flood, what we call a complete flood, or the tank is full of water. So when we look at the orange area that I had delineated in the previous slide, we can see the different changes in the scattering mechanisms occurring around or within the tank from different moisture conditions or water level conditions. We have a full tank where we see predominantly surface scattering. And you can also observe from the last image. When we apply the decomposition, the analysis to get the entropy and alpha relationship of this data, using around 495 pixels. So this the region we selected for analysis within the tank was made up of around 495 pixels. We see there's different observable scattering mechanisms, and this was influenced by the amount of water within that we apply to the tank. So we can see from when the soil is dry, we have more of a double bounce, and as you add moisture, or as we increase the soil moisture content, we observe that there's a change, either drop, we get a drop in backscatter, and then we tend to get surface scattering increase as you go along. So with the 17 centimeters of flood, so this is 17 centimeters of water above the soil, but below the grass. This is observable as you go along, and you can observe from the completely flooded tank, we have reduction in entropy and also alpha angle, and essentially we have more dominance of surface scattering. And then in the different tests when there is no vegetation, we also observe that we start from around volume and double bounce. Then when we add water, we tend to get more double bounce. And then as we increase to partial flooding, we tend to see more increase in surface scattering. And when the tank is completely flooded, we have more, or it's predominantly surface scattering. So these are just some of the preliminary results, and its ongoing work will expand the scope of this analysis so to include all the other results. So this is just L-band from 1 to 2 gigahertz. Then we'll have to incorporate other analysis such as S, C, and X-band. The results of change detection also tend to confirm what we saw earlier. So when we use the first image or the first data set that we acquired when the soil is dry as the reference image, and you apply that to all other images, we see that there's an increase in the dominant scattering mechanism when there's a complete flood, essentially what we saw, more surface scattering for the two. Then there's a kind of a tendency or a trend of increase in scattering as you, in the dominant scattering mechanism as you increase the amount of water in the tank. And there's a drop when there is less water content in the soil. The same is also observable and replicated from the optimization of power ratio. Yeah, when we see the increase in the dominant scattering, the ratio of the scattering mechanism. So these are just some of the preliminary results from the experiment. we anticipate that we'll have more analysis and also more insights in terms of how the SAR signal evolves between a different acquisition and different soil moisture conditions and different frequencies of acquisition. So we'll replicate this to all the 10 gigahertz data set that we acquired and compare that and how the scattering mechanisms change between the different SAR bands that we have. Yeah, these are some of the reference, and yeah, thank you for listening to me.
Thank you, Felix. We have time for some questions. Maybe just one to begin for me. I was not sure to catch if your first results were the colors of the first images were associated to polarimetric channels, or yeah, these ones.
Sorry.
The colors are correspond. Which information is coded by colors?
These are the Pauli RGB.
It's the body. Okay.
Yes. I think one thing to note from this is that I didn't normalize the visualization to be standard or scaled to the same magnitude. So,
yeah, okay. It's okay. Yeah. It was just to be sure.
Yeah.
Thank you. Yeah. Is there any comment? Yes?
Yeah.
No, I'm just wondering, in this plot in particular, in the top middle, how do you explain the variation along range? Or, yeah, in general, because I don't know, it looks like just 1 meter doesn't seem to have so much of an effect, but it seems to be in some of the cases there is a variation in range.
Sorry, could you repeat your question?
No, if you can explain what is the variation in range, for example, in the top middle, that it goes like for more blue to more green.
Yeah. Yeah, I think, yeah, this is something that we need to investigate further. As I mentioned, these are some of preliminary findings. We know there's a phenomenon that is happening when we have more water in the tank. We get to see some scattering outside the area of interest. So it is something that we are yet to investigate and understand further, but I think we can maybe discuss more after this. And it's also something that we need to look into because we also have interference from our targets. So this is something that I need to understand further and maybe find a way of correction within the area of correcting it within the area of interest so that we minimize any effects from the targets, and possibly is to improve the calibration of the data if that could be the reason. So.
Okay, thank you again. If there is no other question, we can move to the next presentation. I think you are still the presenter.
Yeah. Yeah, so, yeah, welcome again to my other part of the presentation. We move slightly further, and besides looking at the experiment or simulated data, now we look at application of SLC, Sentinel-1 SLC data in Rupuruni, Guyana, to understand how we can map flooding in a wetland environment, and in particular to understand how we can monitor seasonal dynamics and identify whether we have areas that have flooding under vegetation. The objective of this particular study, as I mentioned, is to identify any flooding that occurs under vegetation and also understand the seasonal dynamics. So once we have identified this, can we understand the dynamics of floods within this region? The study area is Rupuruni in Guyana. It's quite a unique setting because it's characterized by a vast savanna. And between May and August, when there's seasonal rainfall, some of the grasslands are converted into wetlands for a few months, and this supports rich biodiversity. The area of interest that I'll focus on is delineated by the red rectangle, which is in around the west of Guyana. The key thing here is to try to identify any scattering that would occur or the double bound scattering that occurs under vegetation. You already know that when floods occur in the open, we tend to have more of a specular scattering. And we get more or less backscatter returning back to the sensor, and it's almost established, or there are more established ways of getting this, but the challenge of identifying grassland or flooding under vegetation is what motivates this study. We will apply change detection methods of images acquired between one acquired before floods and one acquired after floods to identify areas of increase in backscatter in grassland region. We utilize the Sentinel-1 SLC data, and for the time series monitoring, we analyze up to around 230 images. And for testing, or for testing of how the algorithm, the methodology we used, we applied PlanetScope imagery or images acquired on a date when the floods occurred. And there are also drone footage or drone images that were acquired in 2020 by ANDREA, which we also utilized to verify some of the land classes or classes of grassland that we had identified from planet images. This is just an example of one of the drone footage that that were acquired by ANDREA in 2020. The resolution of the data is around 5 centimeters with the tiles of 2 by 2 kilometers. Acquired at the Pirara Creek headwaters in North Rupuruni in Guyana. We tested the accuracy of the detection of the different flood types by calculating the area under the receiver operating curve and getting the accuracy and also probability of detection or probability of false alarm. We delineated the regions that were observed from a planet image of flooded area, and we verified some of the classes that we had already identified from drone footage. This is an example of 2 images, one acquired before floods and one acquired after floods. We can clearly see that there is observable changes in backscatter. We have open flood that is almost clearly visible. Then we also have regions that we believe have grassland flooding, although they are not clearly visible. So we tested methodologies, different methodologies, but first we applied existing methodologies that are proposed by Armando. The 2 I had mentioned before. One is optimization of power difference, and the other one is optimization of power ratio, where we get the difference of 2 covariance matrices between 2 acquisitions. Then multiplicative is the ratio between 2 different acquisitions. And then we went further to kind of try to look at models that can generalize changes, the complex changes. And we started by the 2, what we are calling the building blocks, so the differences and the ratios of the covariance matrices acquired between one before flood and one after flood. So the difference is what we're calling PD, and the ratio is what we're calling PR. So we tested different combinations of this signal, of these models. First was to combine by multiplication, so PD and PF. Then we expanded this and whitened using a T2 matrix. I'll not maybe go into detail. Then we simplified that and performed Lagrangian optimization. And the resulting output is a general eigenvalue problem, and we decompose this into maximum and minimum eigenvalues from that. And the two we're calling mon U1 and mon U2, essentially to represent monomial unitary. Then the second one was a monomial combination. So in this case, we are combining with a factor beta and gamma. Following the same procedure, we expanded and then whitened that using T2, then performed optimization. And we tested the different beta and gamma parameters that would give us the best separability between flood and no flood. And the outputs, we refer to them as monomial 1 and monomial 2. Then the third generalization technique that we tested was a linear combination, where we just added the two, so the ratio and the difference with the factor alpha, and expanded that, whitened, and then we simplified this, and the resulting is still an eigenvalue problem. And the output were what we call lin 1 and lin 2. And then the fourth one that we tested, we tried a data-driven approach where we applied the optimization of power difference and got the maximum eigenvalue, what we are calling diff1, after the change. And then we also applied the multiplicative, so optimization of power ratio, and we took the minimum eigenvalue after the ratio. And we combined this in a data-driven approach. And then we combined this using factors M and N, and we tested to identify which is the optimal factor that will give us the best separability between flood and no flood. And one thing to note is that we had the output from this ranges from negative to positive, where we have backscatter decrease will be negative and backscatter increase will be positive. We tested the different factors by one fixing M and either fixing N, and we identified that having a combination factor of 2 for the ratio gave us the best separability of detecting grassland flood and open flood. So we combined the ratio 2 and diff1 to get this. We applied an exhaustive search to determine the factor. So this is just a spatial representation of how the data appeared. So after performing optimization of power difference, we have diff1. We note that areas that have decrease in backscatter will appear blue with the negative values. Then when we look at the ratio, areas that have more change in terms of the ratio appears in red. So when combining this, we are able to get two distinct characteristics. So we are able to identify the blue regions with the decrease in backscatter and the red regions with increase in backscatter. And we believe this is these are regions that the red regions that have experienced flooding under grassland, and the blue regions are regions that experience flooding, open flooding. When we look at how these methodologies perform in terms of the separability of flood and unflooded areas, the ratio 2 was able to identify flooded and unflooded region from optimization of power ratio, and the difference was able to only identify open flood from a combine of grassland flooding and an unflooded area. And the combination, we get this, we may not be able to see, but we get open floods to the negative, and areas that we see have increased flood to the positive, and regions that didn't have much increase are centered around 0. And this is also confirmed by the the confusion matrix. We are able to identify 3 distinct classes because we can apply a threshold in a different way. So one less than and the other positive. And we tend to get some significant good isolation in terms of getting the 3 distinct classes of grassland, open flood, and the non-flooded areas. When we perform the accuracy assessment on this, we note that if we take green to be good and red to be poor, we note that from all the classifications that we tested, the combination of the ratio and difference, the data-driven technique, was the only one that was able to identify areas that had increase in backscatter and what we're calling grassland flooding, with the AUC, area under the receiver operating curve, value of 0.8. And then the combined classes. So we omitted showing open floods because most detectors perform very well in detecting open floods. So we're only showing grassland and the combination of both grassland and open floods. And yeah, the ratio was better at getting both. And one of the methodologies that we proposed, monomio unitary one, was also good at detecting the combination of that. And in terms of probability of false alarm, we tend to see there's significantly good performance in terms of probability of false alarm. Most of detectors have less than 2% false alarm rates. When we apply the detector to the time series, we can observe or we're able to depict a seasonal variability of flooding scenario. What we believe is the grassland flooding, and also the blue, the open flood, and the combination is the red one. This has been overlaid with the precipitation data from CHAPS. Spatially, this is how some of the results appear, or how some of the detectors performed. The detector utilizing VV polarization data was good at detecting open floods. VH detector was good at detecting both open and grassland flood. The ratio 2 was good at combining both, so the ratio 2 combines both open and grassland flood. But the combination of ratio and difference is the only one that we see we're able to pick areas that have increase in backscatter. So, yeah, in summary, we see that there's a potential of these combination methods to identify increase in areas that experience increase in backscatter during a flooding event, essentially what we believe is flooding under vegetation, and also identification of 2 distinct classes. So we are able to distinguish between inundated vegetation and also open flooding. But there's also a need to understand the transition between saturated soil and flooded soil. The next step that we might take, or we are looking forward to, is to test some of these methodologies in using biomass data to identify any inundation in forests. Yeah, thank you so much for listening to me. I welcome any questions.
Okay, thank you, Felix, for the presentation. So we have time for a few questions. Okay, I might have one. So you are combining this additive and multiplicative change. So the question is, what about the physical interpretation? Can you say anything about the physical interpretation of this change?
Yeah, I think this might not be physically interpretable, but we only picked a data-driven approach that could possibly give us areas that have flooding under vegetation, but we cannot physically interpret some of this. Yeah.
Okay. And then another question, because you form this TM matrix, no, with the combination, and then you get the eigenvalues.
Yes.
My question is, have you checked the eigenvectors of this matrix?
We omitted some of the results from all the detectors because they didn't really perform very well as we anticipated and compared to the data-driven approach. So at the moment, I've not looked at the eigenvectors of these combinations, but I think this is something that I can possibly look at afterwards and maybe investigate further.
Okay.
Thank you.
There are no...
You were working with Sentinel-1 data, and there the noise equivalent sigma 0 is not very low, so probably you are affected by the detection of the flooding by the noise level. Did you investigate this?
Not at the moment. I think this is something that maybe I need to look into, because these are just some of our preliminary findings, and I think it's a very good question, and it's something that I have to look into further.
I'm sure this will be a big advantage when you look at the biomass data. So there, the noise is not affecting you so much, so it may be quite trivial, actually, to do what you want to do, yeah.
Yeah, thank you for this suggestion, yeah.
Oh, sorry. Does this kind of change detection only detect flood, no flood? Do you think you could translate the same methodology to other kind of changes like snow, no snow, or crop changes or deforestation?
Yes, thank you for that question. Yes, indeed, these methodologies have been applied before, such as in monitoring crop phenology. I think one of our colleagues also applied it on detecting plastics in plastic pollution in a dam. So the methodology has a variable application, and we can apply it in multiple studies, such as what you're mentioning, snow, no snow, as long as there's change in scattering mechanism between the different images that you have, then that will be replicated in your eigenvalues and eigenvectors. Yeah.
Okay, I think we can move to the next presentation. Thank you again, Felix.
We can welcome the next presenter, who is Georgina Page, presenting the work about using quad-pole multi-frequency ground star data to assess water table depth changes in a controlled peatland bog. Thank you.
Hi, I'm Georgina Page. I am a PhD student at the University of Stirling and giving this talk looking at changes in water table depth in a controlled bog. The other authors I'd just like to mention are Armando, Peter, Jens, Brian and Huama as well. So the main focus of my PhD is looking at peatlands, as peatlands are a really important ecosystem because they store a large amount of carbon in them. And the way they are able to store carbon is because they are often have a very high water level, so they are in a very waterlogged condition. With this, the peat and peat-forming vegetation, such as sphagnum moss, can't decompose very fast at all. The issue is, however, that there are many peatlands that are in a degraded condition. So this is when often the water level has dropped. The land has either been drained to be built upon, or the peat has been dug up to be used for burning instead. So when the water level drops, the peat can decompose much faster, so hence releases much more greenhouse gas emissions into the atmosphere. So there is a lot of work going into restoring peatlands, but one of the key ways to then help do this is to raise the water level back up again. So whether this is filling in the gullies or just creating dams to raise the water level. So my work is our work is looking at assessing how changes in the water table depth can be monitored, particularly to therefore help identify whether restoration has been successful, for example. So the main aim of this particular experiment was to assess changes in the water table depth using a ground radar system, particularly in a controlled environment where we can forcefully change the water level and see the resulting results. Additionally, I was looking at the effect of vegetation on the bogs. So one of our tanks has a lot of vegetation on top, so this represents an area that is in a more natural or restored state. The other one is got very bare peat on top, so with no vegetation, representing more of a degraded condition. This was also a multi-frequency experiment looking at taking measurements in 1 to 5 gigahertz, but a focus on looking at L-band. So the peat that we got for this experiment was taken from the very north coast of Scotland up in an area called the Flow Country. So this was obtained in August 2023 and was kindly provided by a space company, Orbex, who are working in the area. The peat was then transported to the University of Stirling and put into 2 large tanks. So the tanks are 3 meters by 1.5 meters wide, and there is 60 centimeters deep of peat. So the bog on the left, where there is a restored peatland, this has got vegetation on top, such as sphagnum moss, heather and cotton grass, all very commonly found in restored and natural peatlands. And then, of course, the bare peat, where it's a degraded condition with little to no vegetation, representing if peat has recently been dug up or just left abandoned on the side. In the middle between the 2 tanks is this rail where we have moving ground radar gear. So the antennas move along backwards across the rail, taking one polarization, will return to a start, it can change the polarization and continue onwards, taking a full set of measurements. Additionally, the antennas are set on a pivot so that they can change direction to looking at either tank as needed. The radar setup that we have is 2 quad ridge horn antennas. So they have 2 ports in them, so we can get dual linear polarization, and then changing the ports, we can get dual quad pole data. This can take a frequency range from 730 megahertz to 730 megahertz to 11 gigahertz. But we focused on taking data between 1 to 5 gigahertz frequency range, and each set of measurements was in a 1 gigahertz bandwidth. This was all connected to a vector network analyzer, and the data was then collected between March 2025 to October 2025. So this gave 2 years for the vegetation on top of the peat to grow and look in a more natural restored condition. So this gave also a total of 440 images. The data was then processed. We had quad pole data, so it was focused and using a time domain back projection. The images were co-registered, and it was radiometrically and polarimetrically calibrated using 3 different calibration targets, which were in the back of each image. There were then 2 main focuses, 2 main campaign methods that we were looking at. So the first campaign method was looking to simulate almost a drought condition, so where we were draining the peat over time. So to begin with, the water level was at the top of the peat. We took a set of measurements. We slowly drained the tank, took another set of measurements, drained the tank some more, and keep taking measurements, so forth, until the water level was at the bottom of the tank. The other campaign we then did was effectively the opposite, so more of a rain-fed campaign, similar to as you would get naturally, so wetting the tank over time. So while the water level started at the bottom of the tank, we then added water on top until take a set of measurements, and then slowly adding water again until the water level was at the surface of the peat. The other part we did, rather than just taking radar measurements, we also took a number of in situ measurements. So the water table depth was recorded at each of the 4 corners of the tank. There is a white plastic tube which has holes in it, so we had a dipstick measurement of the water table depth. In each of the 4 corners as well, we measured the bog height, and this was to help see the effect, if we could see any effect of something called bog breathing. So this is just natural surface fluctuations of the peat in response to changes in the water table depth. Additionally, we took soil moisture readings across the peat and then general temperature and humidity as well. The main analysis of the results was 2 parts. So one was to help identify if we can see the differences between the 2 bogs and see how the restored bog with vegetation could be viewed differently to a bog without any vegetation in a degraded state. And additionally, looking at changes then in the water table depth. So to begin, we looked at using a number of the known decompositions and calculating their parameters. So Pauli, Claude-Potier, Tuzi, Yamaguchi, and also looking at the intensity, backscatter intensity as well. The other method we used was a change detection method. So this is optimization of normalized difference. So for each individual image, we calculated the coherency matrix, and looking at subsequent dates for changes in this, the coherency matrix gave us the change matrix. Optimizing this with Lagrangians gave the eigenvalues and eigenvectors just to represent the greatest changes occurring between the 2 images observed. For the first set of results, we had looking at how the different tanks can be viewed while looking at an RGB Pauli images. So this first is looking at in L-band, and first can see that there seems to be a difference between a restored bog and a degraded bog. So in the restored bog, there's a larger amount of blue in it, showing that there's a high amount of surface scattering across the bog, compared to the degraded bog, where there is much more double bounce in the red and volume scattering as well in the green. Previous work we've done, we had looked at ALOS2 images, where we only had data looking at restored and natural bogs, and they showed that in L-band that it was very highly dominated by surface scattering and very blue. We didn't, however, have any data looking at any degraded bog for ALOS2 data, so looking at this, you can see that we can see the difference between these 2 bogs in L-band. When looking at in S-band, however, the differences between the 2 bogs aren't quite as noticeable. Both kind of bogs tend to have the blue surface scattering and a large amount of volume scattering as well occurring between them. The other results we are looking at is then looking at how we can assess changes in the water table depth. So this is primarily looking at results in L-band, of where we found the most significant results. Originally, we looked at the known decompositions and those parameters. They didn't show anything significant with looking at changes in the water table depth. So using the change detection method, we focused our ways on. So primarily looking at the first eigenvalue of the change matrix. Each of these points on here is showing the average of the image for averaging around 500 points. This, for example, is looking at the degraded bog, but obviously doesn't seem to show anything significant, whether this is looking at the first campaign in the drought and draining condition, or even in the second campaign where it was rain-fed or watering. The main significant results then occurred when we were looking at the restored bog. So this is where we found that we can see a relationship between the first eigenvalue of the change matrix and the changes in the water table depth. The difference occurs that when you look at the way the method changed the relationship between them. So in campaign 1, when it was a drought condition with draining the bog, there was a negative correlation between these two variables. But when in campaign 2 and we had rain-fed and it was wetting, this was a positive correlation. So combining both of these results together, at the moment we're looking at measuring the absolute water table depth change. This is showing that you can predict, therefore, the changes in the water table depth with the first eigenvalue of the change matrix. We're still looking into why this is, there is the difference between whether you are a positive or a negative change. But at the moment, this result with the absolute change gives an R-squared value of 0.85. A large likely condition which we're looking into, particularly with the drought condition, a lot of the water is being drained from the bottom of the tank, but with the wet rain-fed condition, it's from the water is being added from the top, so it's influencing soil moisture as well more. So in summary, we were able to see that L-band is able to see the differences between the restored and a degraded bog, particularly showing that how a restored bog has a higher amount of surface scattering, and when looking at a degraded bog, it is more double bounce and volume scattering. When looking at the changes in water table depth, L-band is at the moment showing better results, with looking at the change detection method and the first eigenvalue of the change matrix, provided we're looking at the absolute water table depth change. And that's what we're still looking into to help identify the difference between adding water or draining it as such. Thank you for listening.
Thank you. We have time for some questions or comments. If not, maybe a question or comment. Do you think that the change power detection is high correlated to your depth water content because it's mainly a surface scattering? Do you see a link between the physical interpretation of the poly decomposition and the change detection method?
I think there's a slight correlation. Normally, the wetter the bog, there is a higher amount of surface scattering, so it's representing when there is an increase of water, you're getting a higher amount of surface scattering, so that is what the eigenvalue is probably representing in that case. When it's drying out the bog, you're therefore getting more volume scattering. Yeah. So in that case, the eigenvalue can represent that volume scattering. So there's possibly a link between the changes in the scattering type causing that difference as well, which we'll hopefully look into more. Yeah.
Thank you.
Okay, thank you so much for your presentation, and I'm very interested in your antenna to observation of the thing. So my question is, in your lab, there are many targeting outside of the tank, like the frame, the bottles, and also laptop in your study area. So I think, how do you remove this effect when you observe the data? Thank you.
Sorry, could you repeat the question?
Oh, sorry.
Sorry.
My question is, in your lab, the antenna look a large area, and the area had many targets, like the frame, the laptop, and also the bottles. And how can you remove this effect? Because because you only want to observe the information with in the tank, I think. Clear?
If I understand your question, we're looking just at the tank itself, and you're looking at what's externally around the tank affecting the results. Is that it?
Yeah.
Okay. So we did do some test measurements, seeing one, for example, the position of where the tank could influence anything surrounding it. So placing the tank was directly where there was the most minimal effect of anything influencing it. The calibration targets as well are also beyond the tank. So by calibrating them directly, we know that the external areas of the tank are also correctly calibrated, and there's less interference around there as well.
Okay, thank you. Thank you so much.
Anything else? Yeah.
Hi, very nice experiment. I was wondering, I think I didn't quite get it. In the restored, so the second part, right, with the restored bug, what is the strong double bounce due to physically? I didn't quite get it.
Sorry, I couldn't hear you very well.
Yes. In the second case of the restored bug, where you show at the L band the Pauli image, that is very bright red, I suppose. Yes, I just don't quite get physically where the double bounce comes from.
Oh, so the difference here.
Yes.
So part of the theory in the restored bog, there's more vegetation, so it's able to hold the water more, and the vegetation basically helps make the peat more homogeneous, so it's very soft surface with everything in it. The degraded bog, because it often dries out, sometimes it dries out more in clumps, so in that regard, within the peat itself, there are more clumps of peat together. It doesn't hold the water as well to make that homogeneousness. So that's one of the ideas of why there is more volume and double bounce in amongst that, because it's picking up that much more variation in the peat.
Yeah. Thanks.
Okay, thank you again, Georgina. Maybe we can move to the next presentation. Thanks. So, our next presenter will be Jane Skashijian. Sorry for the pronunciation. About soil-borne phenology monitoring.
Yeah. So, thank you for the introduction. Hello everyone, good evening. I'm Sakshi Jain, working at IIT Indore in Satellite and Aerial Remote Sensing Lab under the supervision of Dr. Unmesh Khate and in collaboration with Dr. Vineet Kumar. So the topic of my presentation is multi-crop phenology monitoring using dual pole H-alpha decomposition. So let's understand and let's walk through the history of SAR decompositions and SAR scattering. The first decomposition was introduced by by Chandrasekhar in 1960s, and from then the synthetic aperture radar data. Many professors and many scientists have started working on that, and many scattering decomposition and many scattering matrices were generated. Basically, eigenvector decomposition, eigenvalue decomposition by Dr. Cloud was generated in 1996 based using the quad pole data. Many studies were utilized quad pole data, but very few studies were there for dual pole SAR data. The model-based decomposition, the first model-based, 3-component model-based decomposition was determined by Freeman and Durden, and it was extended by Yamaguchi with a helix scattering experiment. So there are very few studies which utilize dual pole decomposition. Taking motivation from that, the dual pole covariance matrix, which is utilized for dual pole entropy, for generation of dual pole entropy and alpha scattering. So the motivation of this study is that entropy basically measures the randomness of a target, and the scattering angle measures or determines the dominant scattering mechanism. Both can combine together and provides the information about the target's physical characteristics. So my study is earlier for soybean crop only, but it is extended to soybean, corn, and wheat crop. So let's understand what is the dominant scattering for the complete soybean phenological cycle. At the initial scale, when the soybean was just sown and it emerges out, majorly the scattering mechanism, dominates from the surface scattering. And then as the crop grows, the scattering mechanism dominates from dipole scattering, surface scattering, then dipole scattering only, and then dihedral scattering. Similarly, for corn crop, earlier at the initial scale, the surface scattering dominates, then dipole and surface scattering, then dipole and dihedral scattering as the crop grows vertically, and then dihedral scattering dominates. Next, for phenology, the wheat phenology and the dominant scattering, when the seed was sown and after the emergence, majorly the scattering from the surface, and then as it emerges out, as the canopy grows, the surface and dipolar scattering dominates, and then as it emerges furthermore and increases its height in a vertical direction, then dihedral scattering dominates. Then again, when the grain starts growing and the canopy starts further flourishing, then dipolar scattering again flourishes. And at the later stage, the dihedral scattering dominates because the crop was completely in a vertical structure and the vegetation water content lost. Then the dominant scattering mechanism will be dihedral scattering. So the crop phenology timeline for Indian cropping system is that soybean and corn are growing in the Kharif season, that is the monsoon season, rainy season, and the wheat is mainly grown in the winter season. And then the sowing time for soybean and corn is typically at the end of June and harvested in October, early October. And for wheat, it typically sown in mid of November and harvest in March end or early April. So the research question here is the multi-crop monitoring, phenology monitoring can be possible using dual pole H-alpha decomposition. So this is the study area. I have collected a lot of field data for different crop types, that is soybean, corn, and specifically for wheat, soybean, and corn, and some other crops which I have considered in mixed crops. So I have gone through like 1,600, almost 1,600 farm fields personally for crop type information. So this is the LULC map that the study area completely stretched between 3 districts, that is Indore, Ujjain, and Devas. Indore is where I'm belonging from. So the field data that I have collected is shown here. That the soybean data that I have collected in this year from 22nd of August to 23rd of August. And the crop type information for 796 soybean fields and 7 corn fields are there, which is mentioned there. And the crop phenology information for 19 soybean farm fields is there. So these are the 19 soybean farm fields which I have divided into 4 groups based on the phenology at that stage when I went to the field work. The 19 soybean farm fields are divided into 4 groups with BBCH of 65 to 69, 75, and 71. So these are the description that for 4 out of the 19 soybean fields, 4 fields are divided into group 1, 7 and 7 are divided into group 2 and group 3, and 1 field is of group 4 having BBCH of 69. The wheat data that I have collected last year is the crop type information for 602 wheat farms is there, which I have used for this study. And for regular test sites, that for 9 wheat farms and 1 soybean farms, the information that I have collected for those 10 sites, the basic phenology information, the height information, and the other biophysical parameters that I have collected throughout the winter season. The satellite data set that I have used for this study for soybean and corn farms, that is from 26th of May 2025 to 29th of October 2025. In all, 14 Sentinel-1 SLC images were utilized, spreaded from May to October, with a temporal resolution of 12 days. Next, the satellite data that I have used for monitoring the wheat phenology is from 9th November 2023 to 13th of April 2024, with 10 Sentinel-1 SLC images. Due to some issues, some of the data set of Sentinel-1 could not arrive for that particular location. So the methodology that I have followed for this study is just processing the Sentinel-1 SLC data using ESA SNAP software with the basic pre-processing steps of splitting, TOPS split, then orbit file correction, then complex calibration, then TOPS deburst, then covariance matrix generation, multi-looking, and terrain correction. Then all the data sets were resampled and co-registered. And the C2 matrix, that is the covariance matrix, were utilized to generate the dual pole descriptors. And these dual pole descriptors were utilized to generate the that entropy and the alpha angle. Then based on that entropy and alpha angle, the H-alpha decomposition was performed. Other than that, basically the H-alpha plane is typically divided into 9 groups, but I have divided it into 100 zones with like 0. From dividing the entropy into 10 parts and the alpha angle into 10 parts. So the H-alpha plane that I have utilized for this study, or the description of the H-alpha plane, is given in that above figure. The zones that I will be using for the further results that can be understood from this graph. So now I would like to come to the results. That firstly, I would like to represent the results that I have obtained for those 19 soybean fields which are having different BBCH scale or the different phenology for those particular days. So these are the 14 H-alpha decomposition for all 14 Sentinel-1 dates. So these 3 images are for the pre-sowing stages, and these 3 images or these 3 H-alpha decomposition are for the post-harvest stages. So let's understand that the 4 different groups are spread across the zone 1, the zone 3, 5, and this zone 3, 5, and 6 majorly. So let's walk through the mean of these 4 H-alpha value for these 4 groups. That for the pre-sowing stages, majorly the H-alpha values would lie from zone 3 to zone 6. But as the time passes, as the crop starts growing, this is the post-sowing stage. For some fields, it was, for those fields like for group 2, it was early sown, and for group 1, it was late sown. So here you can see that there is a quite separation for the H-alpha values. As the time passes, as the crop starts growing, the H-alpha values can be seen to be separated for all the 4 groups. Here at 11 September, which is the post-pod formation stage, here we can clearly see that all the 4 groups can be kept separately seen. Next, these are the post-harvest stages, and these are the post-harvest stage when all the farm fields were completely harvested. So all the farm fields were at mainly, the dominant scattering for those fields were the surface scattering. So this is a comparison for pre-sowing, post-sowing, and the maturity stage. Next, here I have represented it in the form of maximum pixels, or the fraction of pixels for each group, which are like moves from one zone of H-alpha plane to next zone of H-alpha plane. So here you can see for date 6 August and 18 August, which were the dates prior to the field data that I have collected. So for those two dates, you can clearly see that the fraction of the pixels for each group can be distinguished so that it represents that the dominant scattering is that dominant scattering can be utilized to understand or utilized to segregate different growth stages of a soybean crop. So these are the results. The right side are the results for those 100 zones that I have utilized, and the left side result can be is for the 9 basic zones. So visibly, it is not very much different, but you can see that the H-alpha decomposition plane can be utilized to segregate for separate BBCH scale or the separate phenological stages of soybean. Now the next results come from a comparison of soybean, all the soybean crop fields and all the corn crop fields. So basically those are the crops which are sown and harvested typically in and around the same time. So and the dominant scattering for all those all the crops for the soybean and corn is typically similar for those for the complete growth stages. So here we cannot observe any vast difference among the H-alpha decomposition plane for soybean and for the combined soybean and combined corn fields. So this is the timeline for those H-alpha planes. So nearly all the soybean and all the corn fields have the same range of H-alpha plane, H-alpha decomposition. And all the when I checked with the pixel value or the fraction of pixels, so those are also not, I cannot also distinguish for corn and soybean phenology using this H-alpha. But for wheat phenology, I checked it for wheat crop for all those wheat farms. So it can be clearly understood, or it can be clearly seen that the wheat phenology can be monitored using the H-alpha plane. As the wheat starts growing, the dominant scattering mechanism changes. So the typically when at the pre-sowing stages, when the farm fields were at the preparation stage, the maximum the dominant scattering mechanism is the surface scattering, and as the crop starts growing, it reaches to the dipole scattering and then reaches to the dihedral scattering. So this is the typical phenology of phenology monitoring of a wheat crop for in understanding with the maximum or the fraction of pixels reaching from one zone to another zone. These are for the 100 zones that I have divided. So here is a comparison for soybean. On the right side, you can see the soybean and corn fraction of pixels going from one zone to another zone throughout the cycle. And on the left side, you can see the fraction of pixels going from one zone to another zone for wheat. So I mean, for wheat and for soybean, it can be clearly distinguished using the H-alpha plane that that the fraction of pixels reaching from one stage to from one zone to another zone. So H-alpha decomposition can be utilized to classify basically for wheat and soybean. But in my case, wheat and corn could not be easily classified, but wheat and soybean can be easily classified using H-alpha decomposition. So the key takeaways from this study is that the soybean has a different BBCH scale, can be distinguished using the scattering types. And in this study, the corn and soybean could not be distinguished, but the wheat and soybean or wheat and corn can be distinguished using H-alpha decomposition. In India, soybean and wheat are grown in a separate season, but in some countries like US, soybean and wheat are grown in same season. So this type of scattering or this type of study can be utilized to classify those two different type of crops using dual pole SAR data. So the limitation for the dual pole SAR data that it cannot provide us the complete target information, and due to for low entropy multiple scattering and medium entropy multiple scattering, it has a complete limitation. So the future work for this study that we will understand this, or we will utilize this study for Kansas site where the soybean and wheat are grown for that same time zone. For the same time span. And we will also like to expand this study for the NISAR data with HH and HV polarization for multi-crop classification using H-alpha decomposition. Thank you so much. And
thank you, Sakshi. We have time for some questions. Yeah, Armando?
Thank you. Very interesting. At the moment, you are using only scale invariant information, so it's the normalized one. There is no intensity there. Have you tried also to add intensity? Maybe for separating, say, pre-sowing to harvest. Normally, people use the intensity for seeing these things. Have you tried to add a third dimension, which is the span?
Sorry, can you please?
Have you tried intensity, amplitude?
Oh, so in this study, I have just utilized the entropy and alpha decomposition and the zones only. I mean, in the dominant scattering zones for the phenology monitoring. I have not tried with the intensities only.
That's okay. It may be useful, for instance, to see harvest.
Yeah, yeah.
Normally, people see the drop of backscatterings
Yeah.
where they cut the plant.
So I have utilized the HH and VV polarization backscatter for my other studies, but for not for this.
All right, all right.
Yeah.
Perfect. Thank you. Thank you.
Thank you.
Maybe I have just one quick question too. You use VV and VH polarization with Sentinel-1?
VV and VH, yeah.
VV and VH. And do you still have a physical interpretation to the alpha angle in this case?
So in this case, actually the alpha angle just interprets about the target scattering information. So how for VV and VH polarization, basically when when vertical polarization interacts with a target, then mainly it understands about the vertical structure for that structure.
And do you think there will be a difference with HH and HV, for example? With
there might be difference, but we have not checked it because we don't have HH data right now. But yeah, the NISAR data is released, so I'll definitely try it with NISAR data as well.
Thank you.
Yeah.
There are no more questions.
Yeah.
Okay. So then maybe we can move to the next presenter.
Thank
you again.
Thank you again.
The next presentation will be about surface soil moisture estimation and will be given by Hongtao Xin.
Hello, good evening, everyone. And it's a very good opportunity to introduce my work. My presentation is the high-resolution surface soil moisture mapping from time series SAR over agricultural areas with the constraint of cost resolution soil moisture product. And I'm Hongtao from China University of Mining Technology. I will start with why we monitor the soil moisture over crops, because when we talk about the soil moisture over the crop area, we will several important terms of the soil moisture conditions should be considered. The first one is the saturation of the soil moisture and the field capacity, and also the wilting point of the soil moisture and the situation between the field capacity and the wilting point. It is the information or the ability how the soil can contain the soil water content. It is very important for the crop growth. So, and the monitoring the soil moisture is very important for crop growth. For example, with the soil moisture information, we can increase the crop yield about 10%, and also with the under irrigating or over irrigating conditions, the soil-borne disease will increase. In some areas, the soil-borne disease will rely on the wet conditions for development, transmission, and movement. And also with some more information, we can increase the water efficiency and reduce the irrigation cost. And we also need to note the best soil moisture condition for crop growth is about 16 to 22% of the volumetric soil moisture. In the last 5 decades, the soil moisture is normally monitored with the passive macro remote sensing, like radiation transfer model, and this is we related the Bratton temperature with the soil emissivity to calculate the soil reflection capability, and then we convert this information to the soil moisture. But the passive information had a very cost resolution. It is not capable for the crop monitoring. But with the synthetic radar, we have many advances. Like it is sensitive to the soil diet content and vegetation structure. Also with time series, cold pole, and multi-frequency information, we have the physical and empirical scatter model to retrieve the soil dielectric content. And also we have the polarimetric decomposition model to separate the information from the surface scattering from the volume one. And with this model, we can retrieve the soil dielectric content and then convert it to the volumetric soil moisture with the mixing dielectric content models. And today, the method we normally use one is the alpha approximation method. The idea of this method is use the time series observation with the backscatter coefficient, and also the ratio of the time series, and we can remove or neglect the volume scattering, and also the attenuation with the vegetation canopy. So we use this model, we can relate it to the forward model to calculate the soil dielectric constant. This is the algorithm, the figure, and we can see the time series in the left panel, and also the forward model. We can use the observation matrix and also the forward model vector to calculate, to build the construction, to build the equations, and we can have the solution of the unknown parameters like time series, soil dielectric content. And some limitation of the traditional alpha approximation method is also overcrops. We have these problems. The first one is it needs the high frequency or frequent sub observations. For Sentinel-1, we have 6 to 12 the revisited cycle. And it's period for the crop growth information. It mixed with the soil moisture variation and also the crop growth information. In the last point is for the alpha approximation method, it had an air-post problem to retrieve the many unknown parameters. So we can see the right panel of the time series backscatter coefficient. The colored one is the backscatter coefficient in different incident angles, and the black dotted one is the measured soil moisture. We can clearly see that the measured backscatter coefficient shows the crop growth and also with the variation of soil moisture. So we need to remove the crop growth information. And this is also we can see that the measurement of the crop weight also related to the colored backscatter coefficient. So I do two works. The first one is I want to solve the air-post solution problem. Normally we use the range of 2 to 35 of the soil dielectric constant in natural conditions. But multiple solutions are provided by solving the unknown parameters. My first work is to introduce the prior knowledge of the soil permittivity information from the cost restaurant soil mold product, like satellite disk of CTR cement smooth, as well as the analysis one, such as the EI5 land product. This is the technique how we can calculate the minimum and also the maximum of soil dielectric content from the given cost restaurant product. And the second work is how to remove the crop growth information when it is mixed with the soil moisture change. Here I use the cold pole data, and I introduce the two-component polarimetric decomposition models. The first component is the Asperger model, and the second one is the stepwise volume scattering models from Yamaguchi and Freeman. So the red formula is the information of HH and VV backscatter coefficient from the Asperger model we calculated to, and we use it to the soil moisture retrieval. So here now we can see what we did for the algorithm. The first one is we have removed the vegetation scattering in this time series observation and also the ratio of the backscatter coefficient. And the second one is we introduced the constraint of soil dielectric content in the forward models. So this is the workflow of our algorithm. In the left part, it is the pre-processing of SAR images. We use the cold pole SAR data and coherence metrics, and then two-component parametric decomposition to calculate the HH and VV backscatter coefficient. And in the right panel is how we introduce the cost restaurant soil mold product to calculate the constraint of soil dielectric constant. And what we also want to note that here we have the mixing dielectric content model to convert the soil dielectric content to the volumetric soil moisture. And it has many different models, but we need to evaluate which one is best. So we also did this work. And this is our first study area. In the field scale areas, in the study set is the UV SAR from the SMAP VEX 12. And we have this many different crop areas and also the field measurement. And this one is the soil texture data set from soil grid data center. And this one is the soil moisture content from the cost resolution product. This is 1 pixel of CCR product, and this is the minimum and maximum of the constraint. Let's see our result is this from the HH pole polarization soil moisture estimation result, the time series from June 17th to July 17th. We can see that the variation of the soil moisture is consistent with the precipitation and also different in crop areas. And we also have the VV pole soil moisture estimation result. It's very almost similar with the HH pole, I think. And this is the scatter plot or the accuracy evaluation of our result in different crop areas, like the canola, corn, soybean, and wheat and winter wheat. And the better result is observed in wheat and winter wheat areas, I think. This is the VV performance. And from the MSE or correlation, we find that the HH and VV perform very similar, but HH result performed better. And this is our observation with our estimate. The red dot is the estimation of our method, and the blue bar, the green bar is the soil moisture measurement. We can see that in different areas, our retrieval result is have the same trend with the measurement. But in some areas, also the underestimate and also overestimation with our result. This is the field plot about the resolution. Also, we can see that the red the rigid direction of the soil moisture. This is the plant structure. And this is the weight areas. Well, we think that there are many variations in different places of soil moisture, and also with the time series, time change. It related to the precipitations, and it did the corn areas. And the second I want to talk about is the different performance of using empirical or semi-empirical mixing dielectric models. We here have different models like top and Mironov and John model, also Halikani model. They have different parameters. This is one, normally one, but the different models use different alpha or beta coefficient. This is related to the soil textures and like the temperature and the temperature and the soil texture information. But here we use a different model to evaluate which one is the best in our experiment. Here we show the top. We use the top, the mixing dielectric constant models, and the top one is show the best and better than John model. Like it is similar with the Dobson models. So I think the top model is the best, and it also don't use the temperature, the soil temperature and the soil texture data set. And our second experiment is we use the time series center one data to test whether it is possible to mapping the soil moisture over large scale areas. So we use the time series center one data to mapping the part of North China plant areas. We see that to check whether it is possible to for the global soil moisture product with center one data. And this is the left one is the VV-pole polarization coefficient, and the right one is the merged incidence angles in our research areas. And this is our estimate mapping results. And also we can see that in the July, there are many negative or not very effective areas with the result. It is possible with there are many precipitations or in this season. And also we also find that there are special data continuous of our retrieval result. We can see that this belt is related to the different incidence angles. So the network we did is we used the incidence angle normalization to remove this effect, remove the special continuous effect. And the right one is the map of using center one data with the incidence angle normalization. And this is the scatter plot of our retrieval result with the measurement. And we can see that it has good result, the correlation or low MCE average with the SMAP 1 kilometer product data. And this one is in July. It has a very strong underestimation of our result, but maybe it's related to the precipitation. And to summarize my presentation, we find that time series L-band data, the UAV data, also the alpha approximation method, and as well as the polarimetric decomposition and the prior knowledge of cost resolution soil moisture. It shows great potential for soil moisture mapping at a field scale. And also we evaluated it in the large scale performance. It is good for our result. And also find that the HH pole result is similar with the VV pole, but the former one it performs better. And also the comparison of using different mixing dielectric constant models show that the top 1980 model works best. But also it doesn't need to input the soil temperature or soil texture data set. And the last one is the soil moisture mapping experiment in large scale. We can have this potential to, in the future, to mapping the global high resolution soil moisture in the future. And in the future work, I think we used the two-component polarimetric decomposition model. But in the future, we will refine this model with couple phase difference, because we find that in crop arrays, the couple phase difference is not zero. But we use the model, they had zero phase difference. So maybe this can help us to refine the performance to remove the crop growth information. And the second one is we will, in the future, maybe we will use the Biomass or NISA dataset to use this framework. And also the different penetration depths of C-band, L-band, and P-band also should be considered when introducing the existing soil moisture constraint, because the existing soil moisture constraint dataset is normally very in the surface about 0 to 5 centimeters. And this is what we did about our work. Thank you.
Thank you for your presentation. We have still time for 1 or 2 questions. Yeah, in the back.
Yeah, I already have a mic. Thanks. Thanks for the presentation. I have a question on the first part. So from what I understand, your campaign is over 1 month, but it's roughly a constant phenology for your crops. Is this correct?
Yeah.
Okay. So because the alpha approximation method compensates for vegetation, how do you think your results would evolve if you extended the campaign further?
Sorry, can you repeat your question?
Yeah, of course. So the method, this specific alpha approximation method, from what I understand of it, it's assuming that vegetation doesn't change over time. So this probably stands for your case, because the phenology is rather constant in your time frame. But what if you extended it? How would the results look like?
Actually, in the dataset we use is the UVSAR dataset. It about 2 to 3 days one observation. So in our research area, I think the assumption of the invariant crop growth is worked well for our method. And for the Sentinel-1 data or other data sets like Sentinel-1 or NISA with 12 or 6 days repeat cycle, I think it has some problem. So what we did is we use some method or the technique to remove the crop growth. I think to some extent it can help us to improve our the alpha approximation method accuracy, I think.
Okay, how would a problem look like? I don't have the intuition about how that would look like. So is it that your soil moisture would be very off? Is it that you would have some bias, or what would it be?
Actually, I also have no idea about your question. So I didn't plot the. I didn't plot. I think only the method we can improve is we use the data set measurement to validate the accuracy with different process, I think.
Mm-hmm. Okay, thank you.
Okay, thank you.
Thank you. Please, could you describe the normalization of the radar signal by the incidence angle?
Yes, thank you for your question. And we use a very similar one. Simple one is power of the cosine. In the data, we normalize to the 40 degrees. The cosine is, because we have different angles, the 30 degree or 40 or 42, 45 degree, we use the power of the cosine. Cosine coefficient to transfer the coefficient from 35 to 40 degree. Yeah.
Yes, but the dependence of the radar signal on the incidence angle is not the same for bare soil and for soil with vegetation. In addition, it is high when the surface roughness is high. we cannot use the same normalization independently of this surface. It is not the same for bare soil and for soil with vegetation. And this dependence of the radar signal on the incidence angle depend also on the surface roughness, because it is high when the surface roughness is high.
Oh, sorry, for the normalization, we did have, I have some people also started the different method for the incidence angle normalization. But I just use a very simple one, but maybe it had many problems, I think. Okay, thank you.
Any additional comment?
Yeah, if not, then we can close the session here. Thank you to all the presenters.
Okay.
Thank you.
And we can meet in half an hour for the city tour at reception. Thank you.